voice is breaking up a little bit. Two things we found out yesterday. A, I talked too long. B, everybody was tired. So we're going to change things today a little bit. We're going to end, instead of having after lunch 2 talks, just 1, okay? And that second talk we move to tomorrow morning, okay? So we'll still talk about basic TEM, if I can talk. That's what I was going to do, cough drops. I had a few in my bag, so let me get them now while I'm remembering. And I will apologize if I have to stop every once in a while. Always good to carry some emergency supplies. Although I didn't have as many as I thought I did. And Hamish's will come shortly. All right, so let me stop this one. And start the other one. Window, PowerPoint, open recent, and we want to do number 3. Okay. All right. So yesterday we did diffraction, and we shifted things a little bit differently. Talked about diffraction first, and then imaging. I was trying something different. Sometimes it's better to do one versus the other. Let's see how today goes. All right. All right. You had a lot of the references that I gave you already yesterday. You've already got those. There's a lot of good books out there, and there's even more now. Some of the classic books, as well as some of the newer books. All right. What I'd like to talk about today is imaging per se. And in imaging, we talk about 3 different modes. Amplitude contrast, diffraction contrast, and phase contrast. Amplitude contrast is usually a low magnification image. Diffraction contrast is when we're trying to look at defects. Phase contrast is when we're doing high resolution imaging. So we'll go to all 3 of those modes. We already talked about the microscope per se. We really don't do a lot of work in the illumination system now. We try to get in TEM imaging mainly a parallel beam. The objective lens is fixed, and contrast is now how we orient the sample relative to everything else. So we'll mainly be working with either an under-focused beam or a parallel beam for TEM imaging. And we talked about this yesterday, excuse me. When we're in imaging mode, the post-specimen lenses are looking not at the back focal plane, but they're looking at the image plane. So when we talk about magnification changes, we're changing the projector lenses. And remember, there's multiple lenses that give us magnification. All right. What are the major more than low Z materials? So you'll get basically darker versus lighter, okay? Orientation contrast is diffraction contrast, and we'll be talking a bit more about that. And again, Hamish will also be talking about that and how we interpret it. And then when we look at defects, it's a combination of diffraction and scattering contrast to get the image to analyze it. All right. So most of the things we'll be talking about today are elastic contrast. So we're in elastic contrast is either the amplitude contrast or the diffraction contrast. We're not looking at inelastic scattering. That's this afternoon. Okay. All of these are considered elastic processes. Okay, so let's look at mass contrast first. Mass contrast comes to the fact that different atomic number materials or different thickness materials attenuate the beam that's coming straight through the sample at different amounts. You can think of it very simply. If you've got a huge dense particle, the electrons aren't going to penetrate it, or they're scattered off in wide angles so the beam is not coming straight through. That's simple mass contrast. Diffraction contrast is mainly due to the electron beam coming in and being diffracted away. We'll see how that works in a little bit. Phase contrast is a third thing, and it's an interference phenomenon, and we'll do that too. So again, we're not going to be talking about diffraction. We're going to be talking mainly about imaging, and a lot of the contrast is involving the insertion or removal of apertures, and those apertures are actually put in the back focal plane, okay, because they define which beams come through and assist in creating contrast. So let's first look at elastic scattering in an amorphous solid. We talked about this equation yesterday for diffraction, okay? And we said that we've got the atomic structure factor times some sort of periodicity, which is related to the nearest neighbor distances in the material, okay? So when we plot this function out, we get a function that looks something like this. We got intensity versus scattering angle, and in an amorphous solid, we have this periodic undulation, okay? Now, how do we get contrast? Remember I made the point yesterday, we know a sample is in focus when there is no contrast. Why? Because when the beam hits a sample, it scatters through. If we collect all those scattered electrons back to the image, if we collect everything that went in, we should have nothing. The way we get contrast in this is by restricting the information that comes straight through. And that can be done several ways. The easiest way is by inserting an aperture and at larger angles. So the information that's scattered here doesn't come straight through, but it's off at an angle. Okay? This is a lower atomic number. The information is scattered off at an angle, but because it's a lower atomic number, it's scattered at a different angle. Okay? So if we put in an aperture here, different size apertures, we'll be able to say the very high dark areas are from high angle scattering, and we block that out. The lighter areas are from lower angle scattering, and we get that through. Simple mass contrast, but the mass contrast is due to the change in the intensity distribution with angle. Okay? Did I go the right way? Mass thickness contrast is the most important for biological or organic samples generally. Okay? It's very good for non-crystalline materials. You can, I just described why high Z materials scatter more electrons than low Z materials. They're off at a bigger angle. By using an aperture to block them out, we see contrast. The same thing happens when the sample thickness increases. Can have uniform material, thicker samples means the scattered electrons are further out. Again, we can block them out with an aperture and we get contrast. Okay? So when we talk of a bright field image, what I'm talking about is an image of the electrons that go straight through the sample. And the bright field image is formed by just those that go straight through. It's called bright field because if I look in a hole, it's bright. Okay. Amplitude contrast, okay, is formed, like I said, by the beam coming in, interacting with the sample, and going straight through. Okay. So we have our sample. We can describe that as a simple, the intensity is the wave function coming out times its complex conjugate. And you can write that out mathematically. I'm not going to bother to do it here, but it's simply the intensity that comes in e to a interaction coefficient times the thickness. Okay? The way we get contrast is some of these, if we collect all the electrons, this will be equal to all of that. what we do is in the back focal plane of the pattern, we put in an aperture. So the electrons that are scattered at higher angles are blocked out, and we just have the intensity coming straight through. So it's a simple, in an amorphous solid or non-crystalline solid, it's an exponential in thickness. Okay, here's an example of mass thickness contrast. It's a stained biological material. This is actually a piece of my beard. So we did a cross section. It's the core of the hair, of the hair in my beard. This is not me. This is a mouse. But what we're seeing here is we've stained it. We've got high atomic number in certain areas, low atomic numbers elsewhere. Okay, the thicker or higher atomic numbers are darker than the lighter areas, and you also see very discrete holes, so the beam's going straight through. This is a mouse muscle. Okay, again, it's been stained, so different structures take up the stain differently, and we can differentiate between them by in this case, the atomic number contrast. This area is roughly constant in thickness. It's microtomed. This was microtomed too, but my hair is very brittle. I'll give you another example of mass thickness contrast, this time in a semiconductor device. Okay, this happens to be amplitude contrast. It's a relatively thick semiconductor, but it consists of electrical contacts. So we got silicon, we got tungsten, silicon and copper. Okay, and in this area, they're running current through the device. We got a void formed. Okay, so the void formed, and what's a void? It's a hole. It's thinner. So here we have our copper vial, and we've got a lighter area because it's thinner. Okay. So simple mass contrast, or sorry, thickness contrast. Now, phase contrast is slightly different. We still have a beam coming into the sample, interacts with the sample, and the beam comes out. So we still have that same basic equation. But what's happening now is in phase contrast, we, instead of just looking at the direct beam, we let as much information come as possible. What's happening there? Remember the description we had of the Young's fringe experiment, where we had interference of beams. Well, in phase contrast, it's really an interference of the primary beam and any scattered electrons that come in. Now, this particular example assumes crystalline material, but it doesn't matter. What happens is we get the intensity psi star, and so we have, you can expand that, and if it's a non-crystalline material, we have the first two terms, which we saw previously, but now there's additional terms. Okay? So what we're getting now in the image is not just what comes through, which is that guy, but an interference of multiple terms. That interference gives rise to contrast. Okay, let me give you an example of that. This is a non-crystalline sample. If I, back up, if I put in an aperture and only look at the transmitted beam, that'll mainly be amplitude contrast. If I open the aperture up and allow interference to happen, we'll get additional contrast, and we'll see that here. This is, admittedly, doesn't look very good from here. If I look further back, there's very little contrast there. Okay? It's an amplitude contrast image. There's not a lot there. Why? The sample is carbon, and more carbon, and a little bit of oxygen here. So there's not a lot of contrast. If we remove that aperture, now we start to pick up contrast because we got an interference phenomenon going on. Okay? How can we increase that contrast? We can increase the contrast, back up a slide, by looking at these terms and saying, I want to increase the contrast, so I want to increase the contribution of the additional terms. What I haven't shown you, because I haven't expanded this out, is part of the terms in here have to do with the phase shift of the individual diffracted beams. Okay? Electrons from coming straight through have one phase. Electrons coming off at an angle have a different phase. We can increase that phase shift, and hence the contribution here, by doing something very simple. Defocus the microscope slightly. When you defocus the microscope, you introduce a phase shift between the direct through beam and a beam that's off at an angle. Why? Aberrations. Changing the defocus changes the phase, and that's one of the terms in the aberrations. Okay? So now, here's the same area of the sample for different values of defocus. What do we see? The contrast for very little defocus is weak. As we increase the defocus, the contrast is increasing. Okay? So everybody says, well, let's just work with a defocused image. The problem is, as you defocus the image, we also lose resolution due to, remember we talked about Fresnel diffraction yesterday. Fresnel diffraction is a phase shift, it's a phase contrast. As the defocus increases, so does the Fresnel diffraction. That is what you're actually seeing here, is Fresnel diffraction around the edges of the particles. Your eye likes this because there's more contrast, but it's also defocused. The resolution in this image is actually worse than the resolution in that image. Okay, I'll give you another example of that. This is a polymer. Same area of the polymer. What did I tell you yesterday? Minimum contrast is focus. As we go larger defocus, the contrast increases, either negative or positive. Also, I want you to look at this. That's the same area of the sample. We can go negative defocus or positive defocus. The contrast changes. That's important in TEM, in conventional TEM imaging. Positive and negative contrast change, positive and negative defocus changes the contrast. You will see that in TEM. In a little bit, you'll see, you won't see that in STEM because it's a different mechanism. All right, the other type of contrast, and Hamish is going to talk more about how we analyze this, is diffraction contrast. Okay. Now, how do we get diffraction contrast? Here's a perfect crystal of the sample. Here's a perfect crystal of the sample. There's a grain boundary going there. This area is dark. This area is light. There's a hole. Okay, everything, it's white because it's a hole because the beam's going straight through. In this area of the crystal is oriented such that there is not a lot of electrons that are diffracted off to an angle. So most of the electrons are going straight through. And there is an aperture, I don't show it, but there's an aperture just looking at the bright field beam. Now, in this area, what's happening is the electrons are being diffracted off at an angle. So not all the electrons are going straight through, but a lot of them are going into a diffracted beam. If I have an aperture in there, what happens? Those electrons are stopped, so they don't contribute to an image. The area is dark. So in diffraction contrast, we have alternating areas of light and dark, which we can control by adjusting the diffracting conditions, by adjusting the amount of intensity that's either going straight through or being diffracted off. Okay? That's a big crystal. Here's a dislocation. Okay? Again, a similar principle. This area, most of the electrons are going through. In this area, because of the bending of the planes, we have a diffraction effect, and the area is dark because the electrons that are going there are Bragg diffracted out somewhere else, and an aperture is stopping them from getting back. If there was no aperture, you'd have no contrast. I'm not going to talk about the mathematics of this. We'll leave that to Hamish. But the interpretation of image contrast really can be done. It's more than a 60-minute lecture just on that. But basically, we take the Schrodinger equation. We talk about what the material is made of. We know we've got a wave function coming in. We want to analyze the wave function coming out. And what happens is, as the beam goes through the solid, it goes through an atomic potential. That atomic potential is a function of what's ever in the solid, either it's amorphous, whether it's crystalline, or whether there's a defect. We can model that atomic potential, model the defect, model the crystal structure, put that into the Schrodinger equation, and solve it. The intensity that comes out then is psi star, the wave function that leaves the sample. What is the red dot for? Okay. The other thing that we had is we mentioned that mainly we're in TEM, we do a lot of bright field work. So we're looking at a beam coming straight through. Bright field, we know it's a bright field because when there's a hole in the sample, it's just bright. When we get onto the sample, we get a diffraction effect. It gets dark. A dark field image is just the opposite. We're looking, instead of at the image that comes straight through, we go to the outside and look at the diffracted beams. So now the sample is white and the hole is dark. So when I talk about bright field and dark field, I mean, one, we're looking at a beam coming straight through, one, we're looking at diffracted beams. Now, bright field and dark field imaging are actually fairly simple. We have an aperture that it's called the objective aperture. It's in the back focal plane of the diffraction pattern. We let the beam come straight through. When we want a bright field image, we use an objective aperture to block out all the diffracted beams and just put an aperture around the central beam. That gives us our bright field image. How would we make a dark field image? Well, the naive way of doing it is, okay, I'm just going to move my aperture off to the side. And now I should get an image of just the areas of the crystal that contributed to that diffraction spot. Does that work? The answer is yes. However, remember what we talked about yesterday in terms of aberrations. The aberrations of any lens increase as we go to a higher angle away from the straight through beam. So if you wanted a higher resolution image, you don't want to do an off-axis dark field. What you'd rather have is have that beam come straight here. We do that by tilting the illumination. Remember we talked about the deflection coils. We can either translate the beam or tilt the beam. By tilting the beam, what we can do is we can move, if we want this diffracted beam in, we can tilt the beam one way or the other using the tilt coils and get that diffracted beam right down the optic axis and then form an image. That's a better way of doing dark field imaging. It's called tilted beam dark field, okay? And here's just an example of that. So there's off-axis dark field and on-axis dark field. You can do this. This is the better way to do it, okay? What happens when you do a bright field image? Here's a bright field image using that straight through beam of some defects in a material. This is a gamma prime system in nickel aluminum. Okay, if instead I tilt the beam so that that very weak reflection is now centered and form a dark field image, okay, we have a high resolution image of whatever phase is causing that particular reflection, okay? And in this case, you see what we have is gamma prime precipitates at the grain boundary and small gamma prime precipitates in the matrix. And we also have a dislocation here, which is coated with gamma prime. Okay, I'm going to skip this. We talked about this before. And we talked about how we do the tilting via deflection coils. Oops, what happened there? Okay. The other thing that we can do is do diffraction contrast, and I mentioned this earlier again. We saw this image before. The way we form that image is we have a bright field beam, a diffracted beam coming in, put an objective aperture in, and just form the bright field. This is dark because the diffracted beam's being blocked. Okay. Same thing happens in an image of a dislocation. In this part, we have a perfect crystal. In this area where the dislocation is, the crystalline planes are being bent. And when the beam comes down at a certain point, at a certain angle, we meet the Bragg diffracting conditions. So those scattered electrons are off at an angle. If we put an aperture to block those out, what's going to happen? We'll have a bright area where it's not at the Bragg angle, and we'll have a dark angle where it's at the Bragg angle. There are a lot of other phenomena that happen due to crystalline materials. There are phenomena called bend contours and thickness fringes. Hamish, are you going to talk about bend contours and thickness fringes? I don't remember.
Not really.
Not really? Okay. I'll just go. Okay, I'll just go briefly. It won't hurt you to see it twice. Kinematical theory I'm not going to talk about. We'll just skip it through. What's a thickness fringe? If we have a crystalline material, we can say that the intensity should come through, and I haven't derived this equation. The intensity in a crystalline material will vary sinusoidally with the thickness of the solid. Okay? So we'd expect a sinusoidal variation of the intensity. We see the sinusoidal variation. Okay? We can literally count the number of fringes. That periodicity is related to something called the extinction distance in the solid. Okay. Ideally, we'd expect it to oscillate back and forth. In reality, it oscillates, but gets weaker and weaker. That's due to diffraction, anomalous diffraction in the solid. All right, so here's an example. This is an amorphous material. This is silicon, and we're going thicker and thicker. We can see nice thickness fringes, because if I know the extinction distance, I can tell you how thick each of these areas are. And as we get very thick, they just decay away. Okay. Typical extinction distance, you can look up in the good books or calculate it. Okay, so just to give you a sense, at 100 kilovolts, extinction distances depend on atomic number. Right, the higher the atomic number, the faster the beam oscillates down or gets degraded, and also the higher the scattering vector. These are the different reflections. Okay. And they all vary free between FCC, BCC, or HCP. They're all variable. Okay. Bend contours are another diffraction phenomenon. Okay. A bend contour looks exactly like I've shown you here. How do you know it's a bend contour? It's very easy to tell in a microscope. Just tilt the sample a little bit. These things move all over the place. And we'll see that later probably. Okay. Where's a bend contour comes from? A bend contour comes from that same equation that gave us a thickness fringe. But instead of varying the thickness, I'm going to vary the orientation of the crystal. So we've got pi times the thickness times the orientation. Okay. Now let's pretend we have a uniformly thick sample and it's slightly bent. What's going to happen is the thickness is constant, but we're getting a gradual change in orientation. So what are we doing? We're getting either Bragg diffraction or no Bragg diffraction. And we see that very nicely here. Okay. These are very easy to recognize. Usually if you're right at a zone, we almost see that. You'll see the symmetry of the zone that you see here. If I took a diffraction pattern right from the center of that bend contour, we got a nice symmetric, that's a 110 type pattern. Here's another one, 112. Where are we here? I can't see, I'm too close to it. But you notice each one of these contours corresponds to a specific reflection. G2 is that one. So we can see something about the crystalline solid. It's important to recognize them. I actually use these, if you have a lot of bend contours, you know your sample's distorted. If you have only a few, it's easy, it helps you get close to an orientation, because you don't have to go back and forth between an image and a diffraction pattern. And I've already mentioned that these thickness fringes, sorry, I'm having, die out. So theoretically, they're uniform with thickness, but in reality, they die out, and they die out because of the effective acids decreasing. So they oscillate. It's called anomalous absorption. The other thing that you can get is you can get a uniform sample, uniformly thick sample, but an area of the sample can be shifted due to a stacking fault. So there's an example of a stacking fault. You see a small shift in the planes at that point where the fault is. The kind of contrast you get from a stacking fault looks something like this. Okay, I'm not going to talk about that contrast right now, and it's just well beyond what I want to talk about today. Okay, but stacking fault contrast can be analyzed. We can determine the nature of the dislocations bounding that stacking fault. We can also tell something about the thickness of the sample by the number of fringes. Let's skip that. And so I'm going to skip most of the stuff on diffraction contrast, because that's some of the material that Hamish is going to talk about. I mentioned diffraction contrast, and I bring up just a couple of examples just to show you. This is a subgrain boundary in a material. Why are we interested in subgrain boundaries? Well, we really want to know the nature of the dislocations forming up that same subgrain boundary. And the way you do that is by doing a diffraction analysis, very, very carefully controlling the orientation of the crystal, noting when a dislocation is in contrast or out of contrast where it's invisible. The next example shows you that. Nope, let me just find it. There we go. Okay. Again, a very old image. Okay. This is the same dislocation network. What I'm able to do is by noting when the dislocation is in contrast, that is dark, or out of contrast. Here, I can determine the nature of the Burgers vector of that contrast by noting when it's either in contrast or out of contrast. And I think that's some of the stuff you're going to talk about, right? Okay. So I won't spend any more time about it, but just an example. Now, this is a systematic study. Remember we talked about yesterday how the Kikuchi patterns let us go between different areas of the crystal. Okay. Well, I did that in this particular sample. I think, is that the next slide? No, it isn't. I tilted the crystal. I used the Kikuchi patterns. I found this area. I'd orient the crystal. In this case, I'd orient near 001, okay, 001 axis. And I would orient a diffracting vector. So the 110 diffracting vector was strong. I get a certain contrast. Then the same zone axis tilted a little bit differently. So the 200 was right. Notice the contrast changes. Okay? That dislocation is in contrast there. It's out of contrast there. If it's out of contrast, these particular planes are not in the Bragg reflecting condition. Okay? And by noting when they're in and out of contrast, you can make yourself a little table and figure out what the nature of that Burgers vector is. And again, Hamish is going to talk about that, so I'm going to skip this. Yes. And so remember, I showed you this yesterday. What we just did is we used the Kikuchi lines to orient the crystal and then just get different Bragg reflections. Very, very well excited. I'm going to skip all of this. The same thing holds not only for dislocations, but dislocation loops. We won't be talking much about that now because we don't have time for it today. All right. I'm going to leave that brief introduction to diffraction contrast and shift to phase contrast. And the reason I want to do that is the instrument you have here has an aberration corrector, and it will get you relatively high image resolution. And what I'd like to go over for a few minutes is how to look at phase contrast or high resolution images. It's always, everybody says, oh, I just want a high resolution, atomic resolution image. And they really don't think too much about it. So Hamish is going to talk about diffraction contrast and defects. I'm going to spend a little bit more time here on phase contrast. And remember, in phase contrast, what we do is we look at the scattering of all the electrons that come through the sample. Okay? So in general, we will not have an aperture. We will remove the aperture or put a very large aperture in. Okay. All right. So in diffraction contrast or amplitude contrast, again, we have a very small aperture, and we either look at the transmitted beam or one of the diffracted beams. In phase contrast, we have a very large aperture or no aperture at all. What happens in phase contrast is we have an interference phenomenon between the transmitted beam and each of the diffracted beams. That interference contrast gives rise to oscillations in the images. Okay? So here is an example of interference contrast. It's called a lattice image, but it's just an interference contrast between two beams coming through the solid. So we got a transmitted beam and one diffracted beam. And actually, the aperture, there's no aperture here. It was just two beams in the solid. We get an interference pattern. It's just like the Young's fringe experiment that we talked about earlier. Okay? These lines reflect the periodicity of the two beams that's interfering. Okay? They reflect that periodicity, and that periodicity happens to be due to the atomic structure of silicon because it's crystalline. Okay? Knowing which diffracted beams come in, knowing their spacing, we can work out what the spacing this is. It's also, because we know it's silicon, we can also use it to calibrate. This happens to be the 111 planes of silicon with roughly a 3 angstrom spacing. Okay. Now, there are several ways of forming a lattice image, which is a phase contrast. It's an interference image. You can form it by having two beams coming in, and instead of having you would offset them so they're symmetric relative to the center. Again, that negates aberrations a little bit because one beam and the other beam are equally opposite, and so we get a better high resolution image. We can have a 3-beam condition where we've got the main beam and 2 beams oscillating, or we can have one where we got multiple beams coming in. Now, think about this. If we only have 2 beams coming in, what are we going to do? We're going to get lines. If we, again, 3 beams, again, they're all interfering. We're going to get lines. What happens when you have multiple beams? Well, this is going to interfere with this. It's going to interfere with this. We're going to get a structured image. Okay? So here's an example of a phase contrast, high resolution image of pure silicon. And now I'm letting in all these beams come in. Okay? So I've oriented the crystal. We're getting an interference pattern in all directions. Each of these beams interfering with each other. Okay? We can measure the spacing in each of these directions. This happened to be 110 silicon. So we can derive whatever these interatomic placings are, and we go from 3 to 2 to roughly 1.5 angstroms. Okay. Now, I showed you this image earlier when we talked about instruments, because once we have an image like this, we've calibrated, we know the spacing, we can calibrate the magnification of the instrument. All right. Now, that's all fine and dandy. I showed you a perfect sample, uniformly thick. I gave you a beautiful high-resolution image. Wow. Is that the real world? The answer is normally no. The real world is a sample that doesn't look like this happens to be gold, relatively uniform right up to the very edge, and there's a hole. That's a good sample. Are most of the samples you're going to get like that? No. Most of the samples you're going to get look something like this. It's variable in thickness, there's variable orientation, and there may be amorphous material as well as a hole around it. Now you compare that image to that image, okay? That one looks nice and pretty. That's a nice publication image. That's the real world. Okay. What's going on here? What's going on here is we're getting phase contrast interference, but this area of the sample is multiple grains. So the grain here, although it's a small grain, it's a grain, are interfering in one orientation. This guy's a little different. These guys are even different again. There's defects in the material, and there's also a variation of thickness across this. Also, look at the very edge. It's very different. What's going on there? What's going on there is that we have a variation. I'll just zoom in right on the edge. We're going to look, we get a variation in thickness across the sample. So here's vacuum. Here's the very edge of the sample, the very thinnest part. We're getting a nice periodic image that looks beautiful. Okay? What's this stuff on the edge? That's amorphous grunge that's on the edge of the sample. It could be dirt. It could be just amorphous material. It could be carbon. What is it? We'll have to figure that out later. Now, what's happening here? I've got a nice, beautiful lattice image here, but all of a sudden the lattice image is getting corrupted. It doesn't look very good anymore. What's happening? What's happening is we're changing the thickness of the sample. We're going from a thin sample to a thicker sample to a thicker sample. Okay? And what we're doing is we're getting channeling and interference from different number of planes. Okay? And what we can see is there's a change in how those electrons can penetrate through the solid, and they begin to interfere. And we see that happening as a function of thickness. Can we control that? Not if your sample thickness is varying. Not if the orientation is varying. Okay? So one of the keys to doing good high-resolution imaging is making sure you know what's happening to your sample itself. Let's see what the next slide is. Yes, okay, so this happened. Here's that a little bit even better. So this is silicon. It's variable thickness. There's vacuum out here. There's a little bit of amorphous material out here. And we can see in this area, it's one thickness, and then there's an abrupt change. And notice how we go from white images to all of a sudden they go black. We go back a slide. Oop, wrong one. Okay. What's happening is we're going from white to black. As the electrons are going through, they're channeling and they're diffracting, they're interfering, and we're getting changes in not only the intensity, but also the contrast. So that's a big problem with high resolution TEM imaging. As a function of thickness, as a function of focus, we can get white atoms or black atoms. That's always been the criticism of whenever somebody would come up to me and ask me, well, show me an image of an atom. I said, well, what color do you want it? Do you want it white or dark? It depends on the focus. It depends on the thickness of the sample. Okay, here's another classic example. This is a strontium titanate, lithium manganate sample, okay? If I look at that image, that's a very complex image. Can I straightforwardly interpret that image? Can I say, well, there's an atom there, and, oh, wait a minute, there's an atom there, but wait a minute, what happened here? The atoms are changing. They're not round anymore. They're sort of strange in figure. And I come across here and go, what's going on? What's going on is we got a combination of sample thickness change, sample orientation change, and structure change. All of that's complicating this image. Here's another example of it. This is a nice, clean sample. Notice at the very edge, there's almost no amorphous material. This is more typical. You're almost always going to get a little bit of amorphous material. It could be damage, it could be carbon on the edge of your sample. Okay? And what are we seeing here? We got a nice clean sample where there's nothing on the edge. Almost all of your samples will look something like that rather than that. Getting a good clean image is always difficult. Phase contrast, this interference phenomena, changes with both thickness of the sample, I showed you two examples, but also with the focus. So in this case, we're going from a sample at one focus, and I'm looking at the change with thickness. Okay, now here's the same area, same thickness, but all I've done is change the focus. Okay. What's happened to the contrast? Notice these white atoms have now become dark. Okay, so looking through a high resolution image, just looking at the image, can you interpret it directly? The answer is no. What I'm going to tell you you need to do is you need to do a calculation. Again, we're not going to have time to talk about how to do those calculations. I'll recommend this particular computer program. It's GEMS by Pierre Stelman. He's written a very nice suite of programs for educational purposes. You can get a free copy, but it's also pretty cheap to buy. He's now retired and he just writes the programs and does them. Very good program. What he does is he will divide the sample up. He'll ask the questions I ask you: what's the material? What's the structure? He has a model that he puts in it, and he will calculate how the image goes through, how the waves travel through the crystal, and give you an image of what's coming out the projected potential. Okay. So he will have a model of a sample. From the model of the sample that you tell it what you got, he will calculate the atomic potentials, and from the atomic potentials and the operating conditions of the microscope, he'll get a projected wave function, and from the projected wave function, he'll produce an image. Now, the other important thing that he does in this program is not only does he do this calculation, and that calculation's great, it's up to this point. The beam comes in, the beam comes out. The important thing is, remember we talked about the contrast transfer function of lenses. So in his modeling program, he includes all of the aberrations of the microscope. So you tell him the conditions, you tell the program the conditions of the microscope, wavelength, aberration coefficients, whatever, and he'll put all of that information into the calculation and produce now not a wave function that cleaves a sample, but actually the transmitted wave function that you measure, which is modified by the contrast transfer function of the microscope. Okay? All of these things are included in his calculation. The change in focus, the variation of spherical aberration coefficients, that's all in the contrast transfer function. He'll add chromatic aberrations, spatial coherence, and he comes up with a total system function. Okay? It's a very good program. I highly recommend it. Okay. I'm going to skip this. Why is it important? Because in his program, he will, once you tell it the modeled material. He will generate a series of images as a function of thickness and as a function of defocus. Now you can go to your image and say, here's my model. Here's the thickness that I think it is. Does it match any of these? And you see, this is all the same sample. The only variation here is what's happening to the image as a function of thickness or as we defocus the sample, or defocus the lens. Okay, I'm going to skip this. I'm going to skip this. Oh, yes. Almost always, when you do a high-resolution TEM image, you're going to see nice fringes and something. Okay? Now, I want you to look very closely at that image. We got beautiful fringes. We got a high-resolution image, and all of a sudden, the fringes are coming out here, and they're out in vacuum. How do I get that? How do I get a fringe in vacuum when there's no sample there? The problem is the aberrations of the microscope cause a phenomenon called delocalization. Okay, and the shift of the interference from the actual sample has to do with the aberrations of the microscope. In an aberration-corrected microscope like you have here, this delocalization can be minimized and actually made almost zero. Okay, so the good thing about an image aberration corrector, not only does it give you high resolution imaging, by minimizing the aberrations from defocus and spherical aberration and also C5, you can minimize this delocalization. So now the high resolution phase contrast image matches the structure. That's something that you can see quite easily in a conventional microscope. And this was taken from a non-aberration corrected microscope. Okay, I'm going to skip this bit because it's far too much to talk about today. You've just got a CS corrector on this machine, right? Okay. So aberration correctors for imaging go after the objective lens. This is a image aberration corrected microscope at Argonne. It has both a CS corrector as well as a CC corrector, so it's pretty large. Okay. But it allows you to get very nice high resolution images, both at high energy and at low energy. We're going to skip this. We're going to skip this. Oh, nice. So today we talked about amplitude contrast versus phase contrast. Phase contrast really is more prominent at high magnifications. Amplitude contrast is more prominent at lower magnifications. You get more amplitude contrast there. It's easier to see it. Okay. Let's skip this. I'm going to skip a bunch of slides because a lot of these were too many things to talk about, and we're going to skip it. Yeah, we talked about that. We talked about that yesterday. We talked about that. And I'm going to skip this guy. Okay, I'm moving forward because I want to shift to a different topic. We've talked for about 45 minutes, and I want to go forward. And no, skip this. Okay, I want to go to. I need to change slides here. Excuse me for a moment. All right, stop. That's the wrong one. Cancel this. This one. All right. We've mainly been talking about TEM imaging so far. So we've had a straight through parallel beam hitting the sample, and looked at electrons that were scattered off and formed images. We formed amplitude contrast image, diffraction contrast images, or phase contrast images. There is another operating mode in the instrument called scanning transmission microscopy. The difference, and we talked about this before, is instead of having a nice parallel beam, we have a focus beam. Okay? Is there a reason to go from TEM to STEM? And the answer is yes. Okay? So, are the instruments similar? Yes. Can you get an instrument that does both TEM and STEM? Today, the answer is yes. There are dedicated STEM instruments also that only do STEM. There are dedicated instruments that only do TEM. Okay. Okay. What's the difference between a TEM and a STEM? Not a lot. Okay. We both have a probe. We have a probe. We have lenses that focus the probe onto a sample. Right here, onto a sample. The big difference in TEM is the beam hitting the sample is mainly parallel. The beam hitting the sample in STEM is focused. Skip that. Okay. The nice thing about doing a STEM experiment is when we focus the beam down, we can have multiple detectors beyond the sample. In a normal TEM, we only look at the beam that's either coming through or one of the diffracted beams. By having an array of detectors underneath the sample, we can form multiple images simultaneously. So we can form a bright field image by looking at the beam that comes straight through and hits the center of the detector. We can also simultaneously get a dark field or an angular dark field image by looking at the signal that hits one of the outer detectors. So in the same image, in the same session, we have both a bright field image and a dark field image. Let's skip this slide for a moment. Skip that one. All right. STEM uses the double condenser system to focus the beam on the sample and also uses the double deflection coils to move the sample back and forth. So we have a focusing action by the lenses, and we also have a double deflection system. So the beam scans back and forth across the microscope, across the sample. In STEM, the scattered electrons fall onto detectors. The different in dark field TEM images are usually formed, and I showed you that, by only losing a certain fraction of the electrons. In STEM, we can collect all those diffracted electrons. And how do we do that? Let me go back. Oops. We go back because we have a detector that not only collects the electrons that go straight through, but it could be either an annular detector or a segmented detector and detect all of those electrons. So what are we doing in STEM? We're gathering more signal than we do in TEM. In TEM, we only take a small fraction of it. Now, in STEM, we can get all of that signal and then use it as appropriate. Sorry. Let's see now. I'm going to skip this slide. All right. So, what's the advantage of doing that? In STEM, again, as I said, we have a convergent beam. We have multiple detectors across it. The important thing is the different detectors measure electrons that have been scattered through different angles. Now, what did we tell you early on when we talked about diffraction? We said there's the atomic scattering factor, and higher Z materials scatter things to higher angles, lower Z materials scatter things to lower angles, okay? So the nice thing about STEM is by looking at high angle scattering, we can see high atomic number materials. By looking at lower angle scattering, we see lower Z atomic number materials. It's very easy to get atomic number contrast in this, okay? So in this case, we've got a silicon material with germanium layers in it and a little bit of hydrocarbon sitting on top of it, okay? By looking at the high angle dark field, we've got the high atomic number from the germanium. We see the silicon there, and we can even see some of the carbon contamination. And when we go out to vacuum, if we're looking at an annular signal, not the bright field signal, it'll be black, so it's a dark field image. The other advantage in doing STEM is in TEM, because we have a large parallel beam and a very large beam, we see a lot of diffraction contrast effects. When we go to a convergent beam, we smear those effects out, and we actually reduced the contrast. This is the same area in TEM, STEM, and high-angle STEM, convergent beam STEM. Okay. Notice that's the same area. We can see that same precipitate, and we reduced the diffraction contrast. Why? Because we're smearing it out. We're taking a larger angle. Let's see what's next here. This is what the detector looks like. Let's not worry about that. The detectors in STEM can be various shapes and sizes. Many machines have, many instruments have what's called an annular detector. It's just a circular detector. Modern machines today have arrays of detectors down there. What's the difference? When an annular detector, we're integrating all that signal. We get a lot of signal. In an array of detectors, we can pick and choose which signal we want. The very first STEMs, actually the STEM itself was one of the very first microscopes designed. The very first high-resolution STEM was done by Albert Crew, this guy, and his company, Mike Isaacson, Dale Johnson is back there, and I've forgotten his name, at the University of Chicago back in the 60s. He did the first atomic resolution images with a scanning microscope ever. He had small atoms of uranium on a sample. That machine was a very complex device. It was a 30 kV instrument, lots of power supplies, everything manually operated back in the 60s. And unfortunately, they threw that machine in the garbage. They didn't save it. I would go there every once in a while and say, can I have the machine? No, no, we're saving it, we're saving it. And then one year I went and I said, where's the machine? Oh, we threw it out. All right, how do we get contrast in STEM? Particularly, how do we get this high angle contrast in STEM? It's mainly due to a scattering, atomic number scattering, and Rutherford scattering. Okay. In Rutherford scattering, the electrons come in, they interact with the nucleus of the material, and they're scattered through a high angle. We can show that that scattering angle is proportional, roughly, to the atomic number to a power. Okay? So as long as we're looking at angular scattering, the contrast that we're going to get is inversely proportional to the energy and directly proportional to the atomic number. You write the models, it says it's approximately 2. It's not always 2, but it's a power law dependence. So what does that mean? It means that this scattering cross-section dominates the signal. Notice there's no phase contrast in this. It's just simple atomic number scattering. What does that mean? What does that mean? That means that the images that we collect in STEM, A, the contrast doesn't reverse as we go to thicker samples. B, the contrast doesn't reverse as we change the focus. And we get very nice atomic number contrast. So here's an example of that. This is a lead, antimony, moly on titanium, okay? So lots of atomic numbers, okay? We've got a hole, so it's black. We've got the titanium, which is the light gray. We've got the lead, which is higher atomic number, they're brighter, okay? We can see a change in contrast, and we can get some nominal evaluation of what's present just by the contrast. Brighter areas in annular dark field are higher atomic numbers. Lighter areas are lower atomic numbers. Now, that's a simplification because you also get a change in contrast when it gets thicker. So really the contrast here is a function of atomic number times the thickness. Thicker samples scatter more, so they get a little bit brighter. Higher atomic number materials scatter more, so they're a little bit brighter. So it's really Z times T, and Z to a little bit of a power. Okay? Here's an example of high angle resolution STEM contrast. This is a barium titanate, calcium titanate, okay? So you can see in this case, we've got strontium titanate, strontium ruthenium oxide, and then layers, okay? Let's look at those layers, we'll blow them up. Here's an area of calcium titanate, here's an area of barium titanate. Calcium's lower atomic number than barium. Barium is brighter, calcium is lower. They both have titanium, so we get the same signal from all of them. Let's look at something else. Let's look at some nano gold, and this is in a biological material. We have little particles of gold. Let's go forward. Okay. The structure, theoretically, of this biological material was an array of gold spheres surrounding a periodic structure. That's what we think it looks like. These guys would collapse down to a single point. There are an array of golds. This is not a high-resolution image. This is a very old image. Nowadays, we can do a lot better. Let's go forward. I'm going to skip this for a moment. This is what we can do today in a modern machine. Okay, we've got single atoms, okay, sitting on top of a ultracrystalline, nanocrystalline diamond. These are platinum atoms, high atomic number, on top of carbon. So we've got very small probes. We can see individual atoms. We can see arrays of atoms. We can see crystal structure in there, all with forming this very small probe on a material. Let's go forward. I don't want to talk about this today. With this high angle scattering, remember I told you the nice thing about it is we can form very small probes. We have atomic number contrast, and over this entire field of view, the focus isn't changing, the contrast isn't changing due to sample thickness. Atoms are always the same color because it's Rutherford scattering, not phase contrast scattering. Just examples of this, so we're going to skip forward. All right, I'm getting the point where I've got to stop talking now because my voice is going pretty bad. Let me just see what's left here. I think I want to stop right here. Yeah, we may come back to this later. Let me just see what else is here. Aberrations. Yeah, we don't have a probe corrector on this machine. It's an image corrector, so I'm going to skip these slides. Yeah, we're going to stop here, I think. Yeah, I'm just looking to see what else is here. If there's anything else we should talk about. Confocal, you don't do here. This is all confocal microscopy, so we'll not talk about that. And we're not going to talk about this. Yeah, that's a good time. I need a break. My voice is shot. Okay. So what did we talk about today? Just now, we talked about a TEM image. We talked about the type of contrast you get from a TEM image. You either have amplitude contrast, diffraction contrast, or phase contrast. If you're doing high-resolution imaging, you're doing phase contrast. In phase contrast, you have to worry about a lot of things: the thickness of the sample, the focus of the sample, the aberration coefficients of the microscope. Okay. In amplitude contrast, it's a lot simpler because we're putting an aperture around, we're blocking away diffracted beams, and we get dark and bright areas. Those dark and bright areas have to do with how the beams are diffracted off and how you set up the diffracting conditions. In STEM, we have a completely different contrast mechanism. We can get both a bright field image as well as a dark field image. The nice thing about STEM is that in comparison to TEM, in TEM, in a high resolution image, you can get either a white atom or a black atom depending on how thick the sample is or what the focus is. In STEM, it's not the case because it's Rutherford scattering. The contrast of the image doesn't change with thickness, it doesn't change with focus. It does change, it does get blurry as the sample gets thicker, but the contrast doesn't change, okay? We can form nice small probes. We can get atomic number contrast in STEM. We didn't talk about high resolution imaging in STEM. That's something else that we're just gonna skip for now, okay? I'm gonna stop now because we need to take a break. Hamish is gonna pick up and go back to TEM imaging and talk about diffraction contrast, right? I think that, or is dynamical theory first and then diffraction contrast. And I'm gonna shut up for a little while, okay? All right, let's take a break. How long do you want to take a break for?
we start? Okay, then, yes, good morning, everybody. Good to be back. Thank you, Nestor, for soldiering through that voice of yours, poor guy. So this lecture is about the dynamical theory, and I'm a metallurgist, as you know now. So all questions will be directed to Prof. Sadaka here, who's the physicist among us, the wolf in sheep's clothing. So he's got it. So I know nothing about this topic, so we'll see how we go. And we're going to start with this very complicated diagram here that you know, bright field, dark field imaging. And no, don't be silly. Nestor, this is your thing here. Do I need to turn it on? There we go. Got it. Thanks. Okay. And a lot of the figures I'm using I've taken out of the Carter Williams book, if you want to go and find them yourself, right? So you'll see them. And that's why I've left these the figure numbers on here for you. And the notes for yesterday's lecture and the two today, Nestor has them and he's passing them on their PDFs, so you'll get them if you want them. So anyway, you've heard about this from Nestor. It's not a problem then. And this mass thickness mechanism of observing lighter and heavier materials. We know about that then already. And then we talked about the avosphere yesterday and Bragg's law. I call it a geometrical theory of diffraction. And we can make a small angle approximation of that equation, and we had this yesterday. So you're all up to date on this, right? So that's good. Okay, we did that yesterday. The one thing we didn't talk about yesterday was this vector here, which connects, this is the zero order Lowry zone here, and say this is our, not necessarily a convergent beam, but say if we have a parallel beam with just one avosphere, this would be the deviation parameter from between the diffraction event and the avosphere. And I think you already know from your classes that when we have thin foils, we have these railrods by these reciprocal lattice points that allow us to get diffraction when we're not exactly on the Bragg condition, right? So, okay, so this is all good stuff from. And the other thing we can do is we know that we can orient our electron beam down zone, or we can then pick out what we'll call two beam conditions. And that's even though we've got other beams here, we still call this main, because we've got two major beams, the zero, the incoming beam, and then the diffracted beam in each of these cases. So we're deliberately tilting, and Nestor mentioned Kikuchi maps and so on. We're using those to guide ourselves around the sample crystallographically. One nice thing about these older fashioned microscopes is they have big tilting stages. And the fancy high-res microscopes don't. So a lot of what we want to do here is use an older microscope, and you'll be able to tilt around and so forth. So, all right. And again, this is I'll come back to this later on, and Nestor's already talked about this somewhat, that we can end up with things like exciting plus 3G here and looking in dark field, so we actually get this weak beam dark field. This is the strong two beam dark field, and this is normal imaging in bright field. And it's just by tilting the beam around that we get that. And that would be plus G, this would be minus G, and we have to note that as well. And then I just want to make sure I'm giving you the right lecture. I think I am. We'll go on. So this is a planar slip in Ti 6.4, and we have here this vector S, that's a deviation parameter. When it's 0, it means the evol sphere is going through the reciprocal lattice point. And in that condition, you can see we get a sort of grungy kind of image. It's dark and so on. So that's at the Bragg condition. And then as we increase the deviation parameters, as they're getting greater than 0, you can see now that we start getting the some clearer images, a lighter background, and our dislocations here are dark. This is in a bright field image. And if we continue to increase the deviation parameter, then we start to lose some of this, what I'll call the wiggly contrast. So these are images of dislocations, and you all know that dislocations have a thing called line tension. So it's going to be, they're going to resist the notion of being wiggly. They like to be straight. So something's going on in the imaging that's giving us a wiggly image when we've probably got a straight defect. And that's where the dynamical theory really comes in. And then this goes even much greater than 0. We start to lose then image quality. But you can see that what we've got now are almost straight lines here rather than wiggles. And all we've done is increase the deviation parameter. And so what we can jump ahead and say, okay, this stuff here is dynamical scattering, and this is more like kinematical scattering. So something in the dynamical scattering is giving us these wiggles and sort of fringy contrast. And so, and in fact, we like this because this is really quite an interpretable image, and this is, we're losing image quality here. So, all right, we're getting straighter defects, but we prefer to have the wiggles in terms of being able to do quantitative analysis of these defects. Okay, and then for stacking faults, we end up, say, we have an inclined stacking fault in the foil like this, and we're looking edge on here. And here's an image then, with the beam coming down. And you see we have a set of fringes here, bright to dark. And what do we notice about them? Sometimes we have bright fringes on the outside, and this corresponds to either the top, or the bottom, or the bottom of the foil. We'll see that we can actually determine that. And this is in bright field. In dark field, it turns out there's an asymmetric image. I'll have to show you some image profiles through this, because this is taking an image and then putting it into the presentation and putting it up on the screen here, and we lose detail. But I'll show you what's going on. But the interesting is, you can tell that this is quite bright, and this is quite low intensity here, right? So we have to understand where is that coming from? Why is that occurring? And why do we get the lowest contrast in the middle of the foil? Well, we'll get to that. So, and we say outermost fringe below background in this case. Okay. So we'd like to understand why we have symmetrical fringes in bright field between the top and the bottom, where we have asymmetrical in the bright field, in the dark field image here. And again, we can't tell that from what I call the geometrical theory of electron diffraction, right? Just simply Bragg's law. Okay. So I call this the simple incomplete version. If I can press the button correctly. All right, so we have this. We know what Bragg's law is. And we can have a sample with a bend in it. That bend could be produced by dislocation, or it could just be a bendy foil. And we can say that the amplitude scattered ends up looking like this, where T is the foil thickness and S is the deviation parameter. And so we think, this is kind of looking like an important equation, so that's nice, a bit more complicated for us simple metallurgists. So we think we're on the right track. And this thing here is called the extinction distance. We'll get back to that. And interestingly, this says there should be a variation with the thickness and also with the deviation, with the orientation. All right, so this is now going from the edge of a foil, getting thicker and thicker and thicker, and we're predicting we're going to have fringes like this. Here are the fringes. That's interesting. And then a variation with orientation from this S fact here. And we're looking here, we can see line there, line there, line there, line. It gets rather dark in the middle here, and then we come back to the other side. So we call this a bend contour. Again, it's just a bend in the foil. That's right, that's all it is. And here's the edge of the foil out here. But each of these is, you know, brag 1, brag 2, brag 3, brag 4 reflections as we go out. So you might think that looks pretty good, that we can predict both the change in intensity with thickness and with orientation. Here's the rub. You notice that our fringes die out. So that could mean one of two things, right? The first thing it could mean is we've got a variation in thickness that becomes constant, and therefore we don't really get any fringes. Right, so we're getting thicker and thicker and thicker, and then we're not getting thicker after this. So that means if you're a defender of the geometrical theory, you're going to say, haha, that's what we have. But actually you don't, because when you make a thin foil, it keeps on getting thicker. So we're losing information here that we can't explain by the geometrical thing. And then here, if I were to take a profile, intensity profile from the middle here, which will be the symmetry position going out, when I go through the first maximum here, which is the first dark thing, I have something like this. So my rocking curve would look asymmetric about the Bragg condition here. Why? That's not predicted by the geometrical theory either. So if we look at this equation, it turns out that if we exceed this number here, if the thickness gets thicker than this, then we start making electrons, which is extremely naughty, and you're not allowed to make electrons, right? So there's something wrong with this, and it says that the kinematical theory, what I call the geometrical theory, is valid for very thin foils. And when we start getting any reasonable thickness that we want to look at defects and so on, then it's not really valid. And therefore we have to, whether we like it or not, because we don't like complicated theories, but we have to think about dynamical scattering. We need a more accurate description, and that's the dynamical theory. So in the following, I'm going to go through some equations that if you're like me, you know, your eyeballs will start rolling. But don't worry about it, because you can read it afterwards, and most of you probably know more about this than I do, right? Because you've had good physics at this university. And so let's go, because I'm not doing this to try and confuse you. I want to do this to try and lead you to the point that you understand why we get things like this asymmetrical rocking curve, and why we get dying out of fringes, why we get wiggly images, and so on. And we can understand that from this thing. So we assume that our electrons are incident on the foil in the form of a plane wave. And if we do that, then we have a plane wave like this. This is our wave vector, chi is our wave vector, mass electron, charge electron, and Planck's constant. You all had that before. And what we can do is to solve what's happening to the electron wave in the crystal, we can apply Schrödinger's equation. We can get a solution to Schrödinger's equation. And those solutions exist, so we don't have to make that up. We don't have to sort of work on that. They just exist. So Schrödinger's equation looks like that. You've seen that before. I know all of you have, because you've done physics at this prestigious university. E, in this case, is the accelerating voltage, and V is the crystal potential. So our plane wave is going to come in, it's going to enter the foil, and what's it going to see? It's going to see the crystal potential, right? Which happens to look a lot like atoms, spacings, right? So, of course. And so, we know what the accelerating voltage is, but for this crystal potential, we're going to use, we're going to simulate that with a Fourier series, and we're going to make it look like this. And I'm going to do the usual thing. You all know what these things are. So we had for the electrons outside the crystal, from the previous slide, this expression. And then inside, the periodic crystal influences the plane wave. So this is our plane wave here. And then we're modifying that by this function here, which is called k, or k is the wave vector inside the crystal. Chi was outside, k is on the inside. And this is the plane wave. This is the block function here. The block function looks like this. So it's a periodic function. That's where we're getting the periodicity from. And so we can then go back and say, right, our wave function inside the crystal is going to look like this. And then we can do some rearranging, and so there it looks like that. So here we have an amplitude term. Here we have our wave vector. G is to do with our diffracting planes, as we think, but it's to do with the crystal potential. And R is a positional vector. Okay, so this is a block wave. So this is one of them in the solution. And in fact, in principle, there's an infinite number of them, of these block waves. So, and incidentally, we love block waves, as you'll see, because they tell us a lot about the things we want to know about. So, this is the ith block wave. It has an excitation. To what degree is this block wave excited? And that's that term. This is the amplitude of the ith block wave in the given beam, so either direct beam or the G, 2G, 3G. And then here's our wave vector for that block wave. So you can imagine already that our excitations will vary from one block wave to the next. Our amplitude will vary from one block wave to the next, the way that block wave is distributed across the diffracted beams. And we're going to have a series of wave vectors for each of these block waves. So when you have wave vectors, i.e. related to wavelength, and they vary just a little bit from one of these block waves to another, what might you expect? You might expect some interference effects, right? So, like a Doppler effect, right? And we're going to see that plays a major role, right? So these three terms are very important. I think excitation. So that's the excitation of this block wave. CG, for this block wave, this is how the amplitude of this block wave is spread over the various diffracted beams and direct beam. And then our wave vector, there, wave vector. Okay. And this is all of the ith block wave. So to find a solution, we need to determine the values for the excitations, the amplitudes, and the wave vectors. And that's what we're going to do. It won't be so rigorous, so please excuse me, but I want to get to the point where it's something useful for us, each one of these, okay? All right. So the first thing we want to know is, look, we know, when we look at a fraction pattern, that we have a direct beam, we'll have a diffracted beam, G, first order, second, third, fourth diffracted beam. We know that because we see it in the diffraction pattern. But what's the relationship with these block waves? Is there a relationship between them? Of course there is. So there are in principle an infinite number of block waves, but usually there are only a few that are strongly excited. That's the theta term. All right? So there are only very few that are strongly excited. And, naughty, here we go. There are also an equal number of block waves as there are diffracted beams. So you know when we said we had two beam condition, because we could see the direct beam and a strongly diffracted beam, even though there were little ones around there, so, but we said that's a two beam condition. Well, that's exactly what we'd have. We'd have two strongly excited block waves, and there will also be block waves corresponding to all these other waves. But what is the relationship between them? So here's a thin foil, here's the incident beam, and here is a direct beam, diffracted beam, or second diffracted beam, and so on, right? So that we know that because we see that in the diffraction pattern, right? So that's not a problem. We don't see block waves, right, with our naked eyes, so we're a bit skeptical, right? So where are they? So they're here. So for the first block wave, there is an amplitude of that first block wave in the direct beam. There's an amplitude of that block wave in the G and 2G. So the block waves exist in each of these diffracted beams. So that's how they're spread. So we can also say, okay, there's what we just saw, but actually there's going to be in this direct beam contributions from the first block wave, the second block wave, the third block wave. And each of those is going to have a way that it's got spread across the lattices, across the diffracted beams, diffracted beams. So when we want to say what's the intensity in the direct beam, we're going to add up all the contributions from the block waves, but just their C0 contributions. And each of those block waves will have slightly different wavelengths, because the Ks will differ just a little bit. We'll see what that means shortly. Okay. So this is the metallurgist saying something. Substitute that and that into the Schrödinger equation, yields the result. So don't question me, because it comes right out of the books. So there it is, and you'll see a lot of this you'll have seen before. Maybe you won't realize it's as useful as it is for us here, but we're just going to go through this quickly. So there's k squared equals this. That's chi squared. Remember, chi was the wave vector outside, plus this. And this is the mean inner potential as the electrons enter the sample. So it's like a refractive index effect. So k is the wave vector of the incident electrons after correction for lambda due to the mean inner potential, right, that U0. And so it's a refractive index effect. And we're going to make our two beam approximation. So how many block waves are we going to have? 2, right? So for the direct beam, our equation will look something like this. And you'll notice we have 0 here because it's a direct beam. And also, you notice that we're going to end up by summing them over I here. So that's because we're going to have 2 contributions to there, right? So from each of the block waves. And so we write this. This is standard dynamical theory type stuff. And so now we can get equation like that. For G equals G, we're going to end up with a different set here because we've got K plus G. And these are the wave vectors of our block waves. This is the wave vector of the electrons when they've entered the foil, but they haven't yet started interacting with the crystal potential. All right, so then we can make this matrix equation, and then we can multiply that out. It's going on strike here. So we can multiply that out. And just to remind you of simple trigonometry, or remind myself of trigonometry, and the high energy approximation that our wave vector of our block wave is very much like the wave vector of our block wave plus G, and also of our wave vector K. They're all about the same value, slightly different. So we can then rewrite this equation here like that. Those are 2 Ks. So we can end up with our 4K squared there. And outside the crystal, K is equal to chi. Inside the crystal, not yet interacting, large K is chi squared plus the mean inner potential. And then when they're interacting with the crystal potential, which is when we get our small k's from our block waves, then it looks like this. Right, so bear with this just for a minute. The quadratic, therefore, has 2 solutions. Quadratic. So each of those is a solution for little k, basically, so we have 2 block waves. So we've gone through an approximation of the mathematics and ended up with 2 block waves. So let's introduce our dispersion surfaces. You all remember this from your physics, solid state physics, right? So this is just so here's a dispersion surface, basically. So these are all for low energy electrons in the crystal. But we have this wonderful electron microscope which is producing very high energy. And so when we go to high energy, we end up having to go further out. And these are the interactions. This is the dispersion surface that we're interested in. And if we blow that up, it looks like this. So way down here, these are the wave vectors here. This is chi, this is K2, second block wave. I haven't drawn in the other one for the first block wave. But here we have, this is where, for this orientation, this is where we have the wave vectors for the 2 block waves. And remember what we said we wanted to do was find out about the excitations, about the CGs, and about the the wave vectors. So this is about the wave vectors here. They're shown on this dispersion surface. And of course, as we vary orientation, we're going to vary like this. So these will go out like that there, and out like that there, and be closest there. Okay, so at Bragg, that's where our dispersion surface will be. So our block waves would be, have k vectors here and here on that dispersion surface, on that dispersion diagram. And these red lines would be the capital K, that's the wave vector of the incoming electrons after they enter the crystal, but before they start interacting with the crystal potential. And so these are the Ks, the block waves, when we are interacting, of course. And that's with a positive deviation from Bragg. And so we had that. We'll play with these. And you'll see we're going to put a lot of substitutions in here to keep things fairly simple. So this is K squared there from the high energy approximation. So that's now our equation relating K. And so now we're going to, the first thing is to define this vector gamma. And the gamma is going to equal K minus K. And if you remember that diagram, I'll show you now. That's the diagram there. So there's our gamma 1 and gamma 2. Gamma 1 for the first block wave, gamma 2 for the second block wave. And we're just describing that because it makes it a little simpler to do that. So gammas are now a representation of these the wave vectors, right, for the block waves. So for G equals 0 and G equals G, the left-hand side of that previous equation becomes that. And you can read through the mathematics if you're really interested. But the K minus K is just minus gamma of I, and we have K plus K is just 2K. And so that's that. And we can write that equation we had previously like that. And that's gamma 1 plus K minus S of G. S is that deviation parameter. So it simplifies to that. When I say simplify, it means it's got less terms, right? So it might be more difficult, who knows. Right, but this yields then for our matrix equation that, or just write it in this way. So remember, gammas here are related to our wave vectors of the block waves. That's the description now that we're using. So we end up with this equation, blah, blah, blah. And I want to get to a result shortly. So you can work through the mathematics. In fact, please find some mistakes. And for these, from this equation, we can just obtain this, and that's simple mathematics to get that. So at Bragg, so when SG is 0, this becomes gamma I is UG, plus or minus UG over 2K. All right, so then gamma 1 minus gamma 2 will end up equaling 1 over the extinction distance. And you know the extinction distance is going to have something to do with the periodicity of these fringes that we've seen in the images. And so this, at this deviation from Bragg, this would be 1 over the extinction distance. And obviously at Bragg, I think I'll go to Bragg next. Yeah, at Bragg here, this would be the 1 over the extinction distance here at the Bragg condition. And so we can see that the extinction distance is at a maximum at the Bragg condition and will decrease with change in orientation from Bragg. So if you take your foil, your thin foil, with these fringes, thickness fringes that we saw, and you were to orient the foil to the Bragg condition, that would say that the extinction distance is at a maximum. So there'd be a certain periodicity of these things. If you then started deviating from Bragg, they're going to start running up towards the surface because now the extinction distance is decreasing. So this is a visual, at least consistent with this notion, a visual proof of that. That's why. And you can't explain that by kinematical theory. Oh, sorry. So the thickness fringes observed are a consequence of the beating of two block waves, each with an individual value of its wave vector, but with only a small difference in these values. Now we still have the problem that we're losing intensity here as we go thicker into the foil. So you've got to get back to that. Why is that? So we had that. So again, we can run through some of this mathematics. I'm not going to stop. You can read through these in the notes if you're really interested. That little k minus big K is gamma, and that is 2k from the high energy approximation. So we end up with this equation. So now we're doing another substitution. We're saying let's have a deviation parameter W. There will be the S that we saw. That's the deviation from the evosphere from the diffracting condition, the diffraction point, and our psi G. Okay, so we call this the dimensionless deviation parameter. So we had that. You go back in the slides. So we can now say that our CG1, so now we're looking at CGs here, trying to get some idea of how these values vary, will equal 2 times the exclusion distance times gamma 1 there. So that's the first block wave, and that's the ratio of the amplitude of the electrons in the G diffraction vector or in the direct beam. And that will actually become that. So we end up with this equation. And that's why they've made this substitution, because now that looks kind of easy. And then they have another substitution. They let beta be defined as W equals cot beta. And since we know that the square of the amplitudes, and add that of the direct beam and the diffracted beam, will be 1. This isn't a 2-beam approximation, right? Will equal that as well. Then we can say, using that expression, we can end up with, substituting those three arguments, that's why I named them A, B, and C in the previous slide. We end up with this as our solution. So this is the amplitude in the direct beam of the first block wave, and it's equal to cos beta over 2. And this is the amplitude of the first block wave in the diffracted beam, and it's equal to this. And here we have for the second block wave, we have the amplitude in the direct beam is this, and for the second block wave, the amplitude in the diffracted beam is that. Okay. So the amplitudes of the given block wave in either the direct or diffracted beams. So remember, that's our relationship. So here we have two diffracted beams. We have 2 block waves. And so this is the C0, and that's, of course, the wave vector. And this is the CG. And there's, of course, a contribution from the first block wave and the second in each of these. And that's repeating what you had in the previous page there. So that's what all this means. That's our values for the CGs. So we've got the Ks, we've got the Cs, and how about the excitation parameter? The theta to the I, or the I, it's the ith. Right? Of course, we're just going to have 2 in this case. So these are determined from the boundary conditions. So the amplitude of the direct beam is that. The amplitude of the diffracted beam is that. So we end up with the direct beam at 0 here, which means at the surface, incoming surface, we haven't gone in yet, will equal this, and it'll have a value of 1, the excitation. The phi, and this will be 0 because we haven't diffracted yet at all at the surface. And so we can write this matrix equation from that. So use the diffracted amplitude, C is the eigenvector matrix, and theta is the block wave excitations. That's what we're after. So at Z equals 0, here's our matrix, and it has just 1 value in it. So we can write that, and so we can say that the amplitude of the ith block wave would equal the amplitude of the ith block wave in the direct beam. So we've already got that, knowledge of that, so it tells us, therefore, the excitations are given by the amplitude of the given block wave in the direct beam. So now we've got idea of each of these 3 things. Let's see what's what's going on here. So theta 1 is that, theta 2 is that. Oh, and of course it's important to know excitations vary with orientation, right? Because beta is a orientation parameter. Okay, so they vary with orientation. We define beta as cot beta. Therefore, at Bragg, S of G is 0, beta is pi by 2, and hence at Bragg, beta over 2 will be pi by 4. And what we're going to predict is this. So here's the block wave excitation, right? Theta I against orientation. Here's the Bragg condition here. And so for block wave 2, for a negative deviation from Bragg, we're going to have a decreasing intensity as we go, increasing in the negative deviation. So it's going to go up like this, and this one is going to come down like this. It's going to say, okay, that the maximum excitation for block wave 1 is negative at Bragg, and it's going to decrease like that. And you might say, so what? So let's see what so what is. So consider the distribution of electrons in each of the block waves. This is kind of an interesting thing. So what we're plotting here is here's the crystal lattice here, right? And here's our incoming electrons here, and now we've got the block waves scattered into over this crystal potential. And what turns out is that K1 here, which is the first block wave, it spends its time mainly like this. Its maximum intensity is on these atomic columns here. So what does that mean? That means the first, our block wave 1, is spending a lot of time in the vicinity of the atomic scattering centers. So it's going to be scattered. And when we say scattered, and when we say absorbed, it means that there's an objective aperture that's taking out the electrons. So spatially, our first block wave is spending a lot of time in the scattering centers. Our second block wave is spending a lot of time between the scattering centers. So we're going to say this is heavily absorbed, or heavily scattered, lightly scattered. And that's the first asymmetry between these two that's very important. Why? Because the consequences of this distribution, this difference in distribution, is this. Right? The electron block wave, as I said, spend much time in the neighborhood of atomic scattering centers, so they get scattered. And block wave 2, they spend much time channeling between the atomic centers, and so they're lightly scattered. So let's see what that means. That was the prediction for our excitations, right? That negative of Bragg, we would have block wave 1 highly excited, and block wave 2 very lightly excited, vice versa for our positive deviation from Bragg. So block wave 1, highly excited, strongly scattered. Block wave 2, highly excited, but lightly scattered. So what does the overall rocking curve look like? Because this is going to be called a rocking curve now. And it looks like this. And I showed you that before, right? We talked about so it goes like this. So do we understand that now in terms of the block waves? Here we have low intensity in our rocking curve. Why? Because our highly excited block wave is heavily scattered, because it spends its time in these centers, scattering centers. Whereas our block wave 2 over here is highly excited, but it's lightly scattered. So a lot more intensity here. And you'll notice as well that the peak in intensity is a positive deviation from the Bragg condition. Now, none of that you got from the kinematical theory. And this is something that's really important for us when we're using the microscope. Because we want, for example, if we want to see a defect, as Nestor showed, if we go positive of Bragg, we get a very bright background. And so when we scatter, we'll have a very large contrast between the scattered thing, which will be our defect, and the surrounding matrix. And that's what we want. Over here, and that's why we saw, when we were at the Bragg condition, we saw pretty grungy contrast. And as he deviated from Bragg, it got better and better, right? Because the background was, the contrast offered by the dislocations was increased because of this effect here. Now, again, I'm not a fan of all this mathematics, but I am a fan of understanding what I'm seeing. And we can understand now a lot of what we've already noted we couldn't do with the kinematical theory. So let's talk about this business of block waves spending their time in the scattering centers, say the block wave 1. So as we increase the thickness, it's going to gradually just be scattered and gone. So if you have a beating effect that gives rise to these fringes, and that's between block wave 1 and block wave 2, the reason why we run out of fringes is because block wave 1 is gone. It's been scattered as we get thicker and thicker in the foil. Right? So that's, you can immediately understand that. You can also, we haven't got there yet, but you can also understand wiggly images. It's going to be scattering between block wave 1 and block wave 2. But as you go to thicker and thicker parts of the foil, they start to get straight, the description, because it's only block wave 2 that's giving rise to the intensities. So it's a very useful thing to know about. These block waves are very nice because they teach us a lot about what we're looking at and how to get the best out of the best in the information. All right, how do we account for this? It's accounted for in the theory by including an imaginary component of the crystal potential. So that's this guy here. And even our physics friends have found it very difficult to actually calculate that. And so what they did was they just said, let's put in something like a tenth. Our imaginary potential will be about a tenth in magnitude of the real potential. And then they have adjusted that in the simulations of defects to come up with a reasonable number, right? So that's our imaginary potential. And that's for psi g0, that's for psi g prime there. So it's about a tenth of the real component. And so what you'll see, and I love these profiles because these days you can do it nicely and show a nice calculated image, right? This is the old way of doing it with a profile, right? They calculate. So solid lines of bright field, this is dark field, and this is now looking at how the variation in these fringes will change. And if you look down here, you will see the psi g thing here. So this is 0.075 there of the real component. And this is for a negative deviation, and W is here. This is the dimensionless deviation parameter, and this is about minus 0.02. So you can see that there is an important difference here between the bright field up here at the top of the foil. They're the same sign here, the fringes, and the fringes become the opposite sign. And remember, we looked at those stacking faults. We said there's on one side, it was the entry side, they were the same, and then they were complementary on the bottom. So there it is. All right, and so that comes back to this point here. So let's just see if we can understand this kind of contrast. What are we seeing? We're seeing, and I'm going to show you some image, but here you can clearly see bright outermost fringe there, bright outermost fringe there, right? And dark field that corresponds to that would be this guy here. We have a bright fringe here and a dark fringe there. So this would be the top of the foil here, the intersection of the fault with the top of the foil. This would be the intersection of the fault with the bottom of the foil. But do we understand what is actually happening in the foil, in the scattering? So here's a diagram that explains everything. So let's go through and start here. So here the electrons come in and they interact with the crystal potential, and we have a two-beam approximation. So we have two block waves, D1 and D2. By the time we get down here, all the way through here, we know they're highly scattering D1, so we only get D2, our second block wave. Right? It then sees this fault, and there's a scattering event, which we can explain in terms of the dispersion surface. We're not going to do that just right now. But this then produces D2, gets through, and it produces now D1 prime, which is like D1, a little different, but therefore we're going to get some interference effects here. Let's go over here. It's looks a little more complicated, but it's still pretty easy, actually. Come through D2, D1, same here. it hits the foil pretty close, so each of these is still active, and so then we get D2 prime, D2, D1, D1 prime. But by the time we get to the bottom here, D1's gone, and D1 prime's gone, and then we just get an interference between these two, right? And it's interband scattering, it's called, and it's got these little nice sort of physicsy terms, but we don't need to worry about that right now. And then in the middle of the foil, where basically our contrast was dying out, formed D1, D2. By the time we get to the middle of the foil here, more or less D1's gone. We then scattered D1 prime, and then by the time we get to the bottom, it's just D2. So we get very little interference effects, and that's why the fringes die out. Are you starting to get convinced that the dynamical theory is worth something, right? And understanding these block waves. It's helping us understand what we're seeing and interpreting the information. Oh, and there, hence you get something that looks like this. Using bright field and dark field. Okay. So, this is a computed stacking fault image profile for this particular stacking fault. And we have thickness over side G is about 7, so it's you get about 7 of these fringes. And we have 0.075, so it's getting close to a tenth. And bright field, dark field lines as we saw before, right? And then this is, that was alpha, is plus 2/3 over W. This is minus 2/3 over W. And you can see that there'll be a difference in the contrast because of this alpha here, term here, which is 2 pi over 3. All right. Okay. So what they do is, just to show you what happens, our alpha is 2 pi g dot r, and we consider the problem set up as follows. Here's the incident beam top, and we say when it meets the fault, there's one set of solutions here, and they enter second, just as we saw, D1 going to D1 prime and so on, or D2 going to D1 prime. And so we have to calculate what's going to here and then continuing on to the bottom. So, and I've taken this out of the book for you so you can read this. I know that you're all dying to, but basically this goes through what ends up being giving rise to these equations. I'm not going to spend time with that, but they are there. If you want to read them and go through them, you can do that. What we're really interested is what's the solution here, right? So we can use equation 2420 down here on the bottom left, all right, and to calculate these two quantities. And these values are then the input for slice 2. And so it turns out that the effect of R, the displacement function, so remember the fault, second fault has a displacement vector, right, R. So it's simply to multiply the terms in CG in the lower slice by a phase factor exponential minus I alpha, and alpha is a 2 pi g r. So how do we know that? Right, remember this lovely equation here for our block waves? So we displace the crystal by this vector r, that's the stacking fault. So then our r at the end there is r minus big R, and then our block wave will look like this. Or it'll look like this. You're thinking, we're getting more complicated, don't like this. But you notice we've separated out then this term here. And that is our exponential to the minus I alpha. And that's containing then this term g dot big R in it. And so that term there is the effective CG term. So what was CG? C sub G is the amplitude of this particular block wave in the diffractive beam. And so what we've done is we've modified by having the fault there, and we end up with this effective CG term. And so C naught is not affected by R, because when we have G equals 0, then of course we end up with this factor just being 0. But CG, The CGs will be multiplied by this factor here, right? So our direct beam is not being affected, but our diffracted beams are. And that's why we get this difference in between the bright field, which is symmetrical, and the dark field, which is asymmetrical. And as metallurgists are feeling pretty clever now, right, that we've understood these differences by using the dynamical theory, but coming out with physical ideas of what's happening. Right? We always go back to physical metallurgy. So we have physical ideas that, all right, we understand that we can see in a diffraction pattern, say, two beams. We know then they're two Bloch waves. We know that one of them is highly scattered, and so we can understand some of these fringing effects, and then as we deviate positively from Bragg, why we lose the fringing effects, and so on. So we're doing pretty well. And that is the end of the story. So, if you've got questions, Siddharth will be very keen to answer them, and I will as well. But you might want to think about this, and if you're interested, you can read through the notes and get an idea. But remember, the idea in the end of the day is to have a physical feeling for understanding what you're seeing. And that's why you can't do it just by direct beam and diffracted beam. You do need to have these Bloch waves in mind and understand the interaction of them, and how Bloch wave 1 gets slowly, as you go to thicker and thicker foil, it just disappears, which means all our wobbly images and our thickness fringes and our details on the rocking curve all get squished out because we're losing that beating effect. So it's cool, isn't it, eh? It's really cool. It took me many years to finally step up to the dynamical theory and actually say, we need to use this. And once we did, it was great. Okay, so is it lunch break now? Yeah. And then afterwards we do, Nestor, are you going to lecture first or are you going to wait till tomorrow? My advice is that you should give your lectures tomorrow. Can you give yourself a nice long break in your voice to let it mend? But I can do diffraction contrast first thing. Yeah. So after lunch, get ready for an exciting lecture on diffraction contrast. And use those old microscopes. They're great. They've got nice big tilting stages on them. It's very important. Okay. Babu, welcome. Babu comes from Chennai. So you can imagine he was a little tired after speaking to his family until about 3 or 4 in the morning. So. Anyway, thanks a lot, guys. After lunch.
So we meet at 2 or?
Yeah, should we do that? Yeah.
So you will do at 2 o'clock?
I'll do it 2 o'clock.
So we'll meet at 2 o'clock. Please come sharp at 2 o'clock. Right.
All right. Okay. So this lecture is going to be a little bit about diffraction contrast. And you'll recall from Nestor's talk this morning about the various ways that we can image using these various detectors in TEM and STEM. And this was the mass thickness business. And then we said, okay, what we can do is do diffraction contrast, which means we can set up these two beam conditions deliberately. And then, for example, we might use a 200 reflection, and so it's diffraction by the 200 planes that's giving rise to the contrast. And so if it's happened differentially across the sample, then we're going to pick up some contrast from whatever we're studying. We talked about this. As S is varied, we lose information, and there's more dynamical scattering over here, and you now know why. We talked about it, right? Our dear block waves that are interacting, and we lose block wave 1 as we go to thicker samples, or if we actually deviate from Bragg. So this is the way to set up either bright field imaging. This would be for G plus G, and this would be in this particular orientation, this would be rise to a strong beam here and a weak beam for the minus G. And if you just took that minus G and put it into the middle here, then we end up with a strong G dark field minus G beam. And as we said here, if we actually just brought this guy in, so that's now here, it turns out to be weak, and it's 3G that's at the Bragg condition. And you can work that out by just taking, look, there's 3G there, and hence it's at the diffracting condition. Okay. And incidentally, that's a large deviation there from the 0, 0, 0, and so the image is highly kinematical and not dynamical. We talked about stacking faults and their contrast, and this phase change 2 pi G dot R. We already had that, you recall, so a number of these things, right? So these are our important values of G dot R. Okay, so 0, a fraction, integer and a half. So 2 pi G dot R is 0. This is displacement perpendicular to G. There's no discontinuity in the diffracting planes, and so there's no contrast. And 2 pi G dot R is 2 pi N. Under these conditions, the component of R is in an integral number of interplanar spacings. No contrast. And so then we say, okay, 2 pi G dot R is fractional, and then we're going to end up with our diffracting planes are discontinuous, and we're going to pick up some contrast. And there's a set of fringes, showing you this, and we interpreted this in terms of what was happening to the block waves here and in the dark field. And I will remind you, symmetrical in the bright field, asymmetrical in the dark field. And of course, we can tell what the intersection of the foil is with the top surface, and we know that that's above background there, and that's above background there, so that is the intersection with the top. So we know the sense of inclination of the fault, and that's the important thing there that we need to know. So the sign of the outermost fringe is important, and these are our rules. So bright field, dark field imaging, the bright field fringes are symmetrical, the dark field are asymmetrical. At the intersection of the fault with the top surface of the crystal, the bright field, dark field are similar contrast, and the intersection of the fault with the bottom, then it's complementary. So these are what we call rules that are always fixed, always occurring. So you can tell the intersection, and I say that's because we want to know if it's like this or it's like that. So it tells us what that is. And we make values of 2 pi G dot R as close to 0 as possible. So 4/3 pi is the same as pi over 3. 2/3 pi would be the same as minus pi over 3. So addition to the pi makes no difference. So rules continue. So for G dot R is 1/3, the bright outermost fringe curve. For G dot R is minus a third, the dark outermost fringe will be there. So if we assume R is a 6112, then for G is 002, G dot R will be 2/3, and for 1 bar 11, it'll be 1/3. And so we normally know exactly what our G vectors are, of course. And our central fringe dies away as the thickness increases, and we know why that is, because that's to do with what's happening with our block waves. And so we must know the actual sign of G. So we can't just say it's either bar 1, 1, 1, or 1 bar 1, bar 1. We actually have to know which it is. And then that gives us the correct sign for 2 pi G dot R. And you saw that image. So this is bright field and dark field under 2 different conditions. And there's the reason why. And you'll recall it's just what's happening here in terms of anomalous absorption of one of the block waves, block wave 1. Wunderbar. And you saw that. So we've done this. And how we set up the problem. And you'll be able to read this before you go to sleep tonight if you get hold of the PDF versions. Anyway, so. All right. So on all of this you had this morning. So it was just to recall if I was giving this on 2 different days. Okay, so that's exponential, and that is exactly what's happening here, is the effective CG term. And C naught is not affected by that. Okay, and so we get the asymmetrical profiles. Okay, and this is all from this morning. It's still the same. See if you recall these. Right, so they're using these computer programs to calculate the image profiles. We can manipulate these in these ways mathematically. So the first term is perfect crystal. The second term is independent of the position of the fault. Right, and the third is dependent on T prime, which is where it will show the thickness fringes. Okay, so faults in FCC. Intrinsic faults, like 1/3, 1, 1, 1. That's if we have a agglomeration of vacancies and they collapse into a Frank loop. And extrinsic would be a third, also 1, 1, 1, and these will be interstitials, and these would be opposite sign, once we know what the particular 1, 1, 1 it is. And these are bound by Frank dislocations, these faults. Excuse me. If you form a fault by glide, and it's a 16112, and we know that the Shockley partials that bound that fault. And since 1/3 111 will equal a 6112 and a half 110, then we can unfault our intrinsics. They only differ by a lattice vector, so the contrast will be the same if they lie in 111 planes, since G dot R is an integer or 0 for a lattice vector. Okay. So intrinsic faults. So what we need to know then is how to define the sign of our fault vector here. And so this is defined by the sense of motion of the bottom half of the crystal to make the defect. So in this particular case here, right, so this would move that way, and the bottom half would move that way. So the fault vector defined by the sense of the motion of the bottom half of the crystal to make the defect. So G equals 1/3, bright outermost fringe. G equals minus 1/3 is a dark outermost fringe. So if G is 1, 3, bar 1, and R is a third, bar 1, 1, 1, then G dot R is a third. So then experimentally, we record the image at S is equals 0. Why? Because with these faults, it maximizes the contrast, both in bright field and dark field. We reverse the sign of G and repeat the dark field and bright field imaging. And then we determine the intersection with the top of the foil, and so we know what the inclination of the fault is. So let's say we have, this is our fault vector, 1, 1, bar 1 here. There are images there, and here's our diffraction pattern. So let's analyze these. And as I told you, producing them here, it's okay. I think we're there. Okay, so the contrast that you're seeing here has been degraded by the fact it's come from a negative, been scanned in, it's been produced here, it's been projected. So I've taken on the nicer images, I've done a profile here so you can see that. Okay, so that would be the profile from A, and that from B. So B, you can see, has outermost fringe is bright. I mean, this guy here. And the outermost fringe would be dark. And C is then dark field, so it's going to be asymmetrical. And D is dark field as well, and that should be asymmetrical. And it sort of is. Comes down here and up there. So for A, the bright outermost fringe is dark. And so if R is a third 1, 1 bar 1, as we suggested, then G dot R is 4/3, and that's equivalent to 1/3. So the bright outermost fringe would be the wrong answer. So therefore R is 1/3 bar 1, bar 1, 1 in that case. And so the fault is actually extrinsic in nature. So we're able to tell something about the nature of the fault from that. This is a sort of 4 faults in silicon. We have A, B, C, D I've marked on there. And A looks like that. B looks like that in terms of... So for fault A, oops, don't you yet. It's either plus or minus 1/3 bar 1, 1, 1. So if we assume it's 1/3 bar 1, 1, 1, then G dot R is a third, so it should be a bright outermost fringe. And that's consistent with the experimental observation. Let's go back here. So A, you can actually see it here, that it's a bright outermost fringe here and here. So, so it should be a bright outermost fringe, we say it is. And so therefore this is, then it's consistent with, if we look at the stereogram, right, for this beam direction, a fault vector of 1/3 bar 1, 1, 1 is an upwardly facing normal. And so the fault must be intrinsic. And in fact, I marked that on there. This is an intrinsic fault here. Okay, so for fault B, you can see my bars have moved over, so it's 1/3 bar 1, bar 1, whereas for that orientation. So we assume it's a 1/3 bar 1, bar 1, 1. So G dot R then is minus 5/3, which is the same as minus 2/3, which is the same as a third. So that should be a bright outermost fringe. And we say this is not consistent with the experimental image, and because it's dark outermost fringe, so, and hence this or that, in actual fact, should be the vector. And so, again, if we look at the stereogram, for this being direction, the 1/3, 1, bar 1 is a downward-facing normal, such as the fault must be extrinsic. So we have an intrinsic, an extrinsic, and for fault C and D, we have a 1/3, plus or minus 1/3, bar 1, 1, 1, G dot R is -1, and for RD, for the D fault, 1/3, 1, 1, 1, 1, 1, G dot R is 1. So these faults should be invisible. So why can you see them? Right, we have integers for the G dot R's, so why are they visible? So we'll take a look and see the scan looks like that. It's kind of interesting. And D looks like that. So sort of not normal looking kind of faults, right? Not symmetrical in any way. So why do you think you're seeing them? So what we're assuming is we have a particular fault vector. And so what we have here is an incomplete fault vector, and so we have a supplementary displacement here because of the bonding in silicon. And so why do we see contrast? Contrast due to the presence of supplementary displacements. The hard-seal model is not sufficiently exact. So by doing these diffraction contrast experiments carefully, you can tell quite a lot about your defects. I mean, here we've discovered that in fact where there should be no displacement at all, there's supplementary displacement. And that's something to know about your sample. So there are other planar defects that you might see, the pi fringes. This is the case for G dot R is 1/2. And so alpha is pi. So images with S equals 0. Again, so for images for S not equal to 0 are complicated. So when the S is 0, bright field and dark field images for a given G are complementary. Bright field, the central fringe is bright, dark field, the central fringe is dark. And fringe spacing is the extinction distance divided by 2. The intensity of the outermost fringe is determined by the foil thickness. So in bright field, the outermost fringe is dark if the thickness is n times the extinction distance. Dark field, the outermost fringe is bright if the thickness is n plus 1/2 times the extinction distance, where n is an integer. So a little complicated. New fringes associated with an increase in thickness are formed at the intersection of the fault with the fault surfaces. So they actually work very differently from the faults we've been discussing. So consider an APB in a B2 structure. R would be a 1/2, 1, 1, 1. No contrast is observed when imaging with a fundamental reflection. So let R equals a 1/2, 1, 1, 1. Then when G equals 1, 1, 0, G dot R equals 1, we have no contrast. And when it's 1 bar 1, 0, G dot R equals 0, we have no contrast. And when imaging with a superlattice reflection, so if R is a 1/2, 1, 1, 1, then if it's G equals 1, 0, 0, we get G dot R is a 1/2, so pi fringes. And if G dot R, if G equals 1, 1, 1, G dot R is 3/2, which is the same as 1/2, we'll see pi fringes in the stuff. Didn't have an example to show that except for found this in APB faults in titania, and you can look at these and see something about the rather complicated contrast here for pi fringes. Delta fringes. These are weak fringes caused by supplementary displacement, as we saw in the faults with silicon. And this is for APB faults in gallium arsenide. And these APBs are inversion domain boundaries, so 180-degree rotation of one part of the lattice with respect to the other. And the translation is caused by the difference in bond lengths between gallium, and arsenic. So it's not a lattice translational vector. And by image matching, computer experimental is determined that the displacement vector was 0.19 angstroms, normal to the fault plane. So you can still get some information that might be very interesting to you if you're studying this material. Again, by carefully imaging in a sort of controlled manner here. to get these image conditions set up correctly. Okay. So back to this to remind us that we can get a number of different diffraction vectors in each of these zone axes. So two beam conditions. We recall that we can go for strong bright field, strong beam, dark field, and we can go for setting up the 3G condition for weak beam, dark field imaging. So let's think about displacements about a dislocation. So there's a nice edge dislocation. And we'd say, let's say you have the diffracting planes as I've shown. The Burgers vector here is looking like this. And so the major shear around that edge dislocation is parallel to the Burgers vector. And there is another contribution, and that is this B cross U term, which are displacements like this around here. And in a screw dislocation, we don't have that. We just have the displacements parallel to the Burgers vector. So that's just a general view here, that we have the Burgers vector and then this B cross U term contribution. And the screw will be much more simple than that. It's just parallel to the Burgers vector. So, of course, if we have a dislocation, then we have continuous displacement fields. And so at some distance from the dislocation, we'll pick up some information here, some distance from it. So, again, the bottom expression there is for a screw, just got the Burgers vector. And the effective displacement looks like that in terms of distance from the dislocation. So obviously there's a lot of displacement very close to the dislocation, but as you go away from it, it decreases. So, and the displacement of the lattice, right, so which is going to affect our diffracting condition, then is given by this expression here. Okay. So this is the effective displacements on the local S value. Okay, it's a kind of complicated diagram, but we have the EVOL sphere there. We have the end of our diffraction vector is here, and then this is now being pushed out to here by the displacement around the dislocation. So contrasting screws and edges at S equals 0. Let's take a look. So this is the calculation for a screw dislocation. So it's computed. We've got solid line is bright field. The broken line is the dark field image. And so you're going to have both cases, you're going to have a dark image here. This is G dot B is 1, and we have a 0.1 for the anomalous absorption here. Okay, so that would be for a screw. For an edge, it's going to look like this. And again, same thing. Bright field image is the solid line, and the dashed line is the dark field. G dot B is 1. So for both edges and screws, we'd say that G dot B equals 1 is going to give us a single dark image, which is, of course, this contrast intensity decreasing here around the dislocation. So contrast from dislocations, S is got a larger value. It's deviated from Bragg. So here it's, what have they got here? Where G dot B is 1, and our dimensionless deviation parameter is 0.3, and we still have a dark image here. But interestingly, we have on the one side of the dislocation a higher background here compared with this side. So we'll need to think about that in a minute. So here are dislocations. Nice image. Right, this is silicon iron. And what you should notice is that right? We have the dislocation lines, that's good. But why have we got a darker gray there and a lighter gray there? Darker gray there and a lighter gray there. Darker gray there, lighter gray there. Why is that? And that is simply because if you note this dislocation, for example, here comes around and back, and around there and back, and around there, and this one comes back. So this is just simply that you have on the one side this, and then if I mirror that, it'll be below background, or it will be above background if there's another dislocation here. So these are just dislocation dipoles here, right? So they're just switched. And so the below background here would be this one with another dislocation here, and the above background here between these two would be this side here, and one mirrored, and then the high background intensity. So immediately you would say those are dislocation dipoles, and you'd be correct. Contrast from segments near foil surfaces. Okay, so all of these really squiggly bits here are steeply inclined to the foil, and when they get near the surface, you really pick up the information right near the surface, close to the surface. So if you're a lonely dislocation in a thin foil, when you get close to the surface, you have image forces that are waking you up like that. And then when you're inclined to the surface, of course, you get a lot of the dynamical effects then that are giving rise to the fringes. Remember where the fringes come from. They come from our block waves. And so if you sit down with the notes, you can work your way through each of these to work out what's happening as you get closer to the surface. So one, if I get back and read this properly. Yeah, 1, 2, and 3 refer to different positions, right? Y over sigma g, right, with respect to the foil surface. And so, again, all that's really happening is our dislocation's in the middle of the foil, it's heading towards the surface, and then it abruptly gets caught up with an image force and scoots up towards the surface, and then we get this oscillatory effect. All right, contrast from dislocations with G dot B is 0. All right. So these are loops here, and this says we have, these are dislocation loops in zinc. We're imaging with a G such that G dot B is 0. Okay, so there's our displacement for these dislocations, that it's a component B and B cross U, so they're edge dislocations, edge loops. And so what are we seeing here? We're seeing a double image here, a double image here, and then almost nothing here. So what is that telling us? So we said we're imaging with G dot B as 0, right? So we think this all should be out of contrast. And the only place it's really out of contrast is here and here. So what we're seeing is that this B term here is out of contrast all the way around. This lot is a contrast from B cross U. And this lot here and here, the G dot B is out of contrast, and the G dot B cross U is out of contrast as well. But so these are just basically residual images here, because it's giving the information is coming from the B cross U term. But this is exactly where the both the G dot B and the G dot B cross U are equal to 0. So we know that this is basically a G dot B 0 type image here for an edge dislocation, which is good. We know that. And so these are calculations of exactly that, what you can see. And so these are just computed for that. The M here is G dot B cross U divided by 8, and then they have different values for the M. Okay. But this is a very characteristic image that we'll see shortly in other cases. Okay, so again, dislocation loops here, and these are the calculations of what these should look like. And we have, of course, if you imagine this is now mirrored on the other side, we're going to have two of these, one over here and one over here. So as soon as you see this image here, you know that G dot B is 0 and G dot B cross U is 0 here and here, but not here. So it's a very characteristic image. Very immediately you can say, oops, say something. And these are more up-to-date, not very well projected here, images, but it's actually calculations where you can now see what we call the double dotted contrast here, which tells us that we have a G dot B 0 case where we have some residual contrast. Okay. How about contrast from dislocations with G dot B is 2? Let me just remind you that clearly we have a double image here, right? Double image here. And that's because that's where the G dot B cross U contrast is, non-zero. So this is now, but for the rest of the loop, it's G dot B is 0. This is G dot B is 2. And what we have is, on either side of the 0 here, as we go away from the center part of the defect, we end up with these two dark images here. Here's the background. So we've got two images there, and this is now, this is at G dot B is 2 with at the Bragg condition W equals 0, and this is dimensionless parameter, deviation parameter 0.3 here, so we've gone away from the Bragg. So here we get a dark image and far less of a dark image there. So as we deviate from the Bragg condition, we're losing this part here, and it comes mainly to a single image. So then people will say, if I get a double image from G dot B cross U not being 0, and I get a double image when G dot B is 2, how do I tell the difference? And the way you tell the difference is that you will deviate from Bragg, and in this case, you'll wash out the one side here and go to a single image. In the other case, it'll just get weaker and weaker and weaker, but you always have the two images there. So you'll be able to tell very clearly if it's G dot B is 2 or if it's G dot B is 0. Okay, contrast some loops and dipoles. All right. So let's have a look at this. So we have here an extra plane here, shoved in here. So that's an extrinsic fault. Here we have an intrinsic fault. This is inclined like that, that is inclined like that. This is now the same inclination here, same inclination there, but if you look here, this is the G vector here for this case, and this is the G vector here for that case. So let's have a look at this carefully. These little twisty signs here are when the beam comes down, it sees this here, what it's seeing is that that's happening to the plane. That's the twist that's happening to the plane. And here, that's happening that way around. And if we look at the G vector here, anything that looks like an anti-clockwise thing is going to push this G vector into the Avol sphere. And then we'll get diffraction. So I'm looking for then anything that does that. So that would give rise to the diffraction. And that would give rise to the diffraction. That would give rise to the diffraction. And this would give rise to the diffraction. So I'm going to get information from there and there. and that would be outside contrast. And I get it from there, and that would be outside contrast. So both these cases, where we have the extrinsic fault is like that, the intrinsic one is like that, we'll get outside contrast for this particular value of G dot B. Over here, what I'm going to do is anything that gives me a clockwise tilt, rotation, will push the G vector into the evol sphere, and I'll get rise to diffraction. And so anything, I'm looking for this then to occur here. So this would be the clockwise rotation. So if we look, here's the rotations here. So clockwise would look like this and this over here. And those would be that and that. So those will give rise to inside contrast. And likewise here, we're going to end up with inside contrast. So we have basically a sort of set of rules here that if we know the sense of inclination of the fault, then we have G dot B is positive. G dot B S will be, let me show you this. Okay, so the dislocation position depends on the sign of G dot B S. And these are G dot B S is greater than 0. We have outside contrast. G dot B S is negative. Then we have inside contrast. So these are rules that we can, if you spend some time looking at that, you'll see that that is the case, that we have the inside and outside contrast. These are a set of dislocation dipoles in copper, and you can see it's imaged with G or minus G, and here the separation is small and here the separation is large. So you can immediately tell that that's a dipole because we've got plus minus G, and if those were parallel dislocations, then it would just be a shift of the image and they would be the same width. Width wouldn't change, but the width changes if it's a dipole because they move in the opposite directions. So, contrast some loops then. We say that this is the relative idea. That there are positions depending on the values of your beam direction, your plus minus B, and whether you have inverted contrast, so you want to be in this area here, but that almost only occurs in very few cases. So if we want to say, right, what is the nature of a loop? Is it intrinsic or extrinsic? Then we're going to look at the inside-outside contrast. So the first thing is we're going to determine the Burgers vector. So these two images, you can see you have dark contrast all the way around this loop. So that's not out of contrast. Here, it looks a bit like we're losing contrast there. And I've got another one down here, 2 bar 1, 1 here, and you clearly have this thing. So this is the G dot B cross U term. So this is basically out of contrast. G dot B is out of contrast, so we can tell that our Burgers vector is plus or minus a half bar 1, bar 1, 1. And so we'd like to know what that is then. So we do the inside-outside experiments. So that means we do bar 200, 200, bar 1, bar 10, and 110, and then O bar 20 and O20. So each one of these are pairs. And we will look at the eeks. Oh, I've just done the, you can see the inside and outside. So with bar 200, we have outside contrast. 20, we have inside contrast for those loops. For bar 1, bar 10, we have, it's very difficult to see, but you might say it's just about outside there and outside there. So these are real examples. So again, outside there and outside there. So outside contrast of bar 200, O bar 20, and bar 1, bar 10. Outside contrast for that. So for bar 200, and assume that we have half bar 1, bar 1. And note that for S is greater than 0 for these images, right? That the S is greater than 0. So our G dot B S is above 0, is positive. And so these loops are interstitial in nature. So to see that, if you're interested in really seeing that, let me go back here. We go from here, where we define what we're getting in terms of outside and inside contrast, what you've got to notice is that this is naughty. The version I had before had the Burgers vectors marked on here, but okay, but what we have here is the Burgers, there they are. Burgers vector is up in this direction, and Burgers vector is in that direction for these, up in this direction and down in that direction. And so that's how you then come to know that when I go forward now, and I first determine the Burgers vector, and then from the information here, from these inside and outside, so, and then I make my assumption that it's a half Bauer-Bauer 1, and we know that S is above 0, greater than 0, so for these images, G dot B S is greater than 0, and from that then, because we know what the sense of the Burgers vector is, it's headed upwards, rather than not downwards, and so these are interstitial in nature. So that's the kind of information that you can get by doing quite simple plus minus G experiments, and then determining whether the contrast is outside contrast or inside contrast. Okay, so this was the G O bar 2 O in this bar 1 O 2 beam direction. And okay, so what this is saying is that we're in this clear thing with a half Bauer 1 and a half Bauer 1. So just to check that we're not running into some inverted contrast situation. Okay, contrast from partial dislocations then. So kind of interesting. So you can see here we have a dislocation on one side here. We have fringes, and then we don't seem to see anything here. Nothing there, some fringes, and then obviously a defect there, a defect there. So it's kind of missing a defect on most of these, around here and here. So what's happening? Why are we missing a defect? And if you calculate what these things should look like, then you essentially, anything with G dot B is a third or minus a third, unless it's essentially it's essentially invisible. And that's what is here. There is a defect there, it's just that it's not visible in the contrast. Whereas on the other side, they're clearly visible here. Okay. And so that's the particular setup there. And you can show that these things are rings. This is of course, the two Shockley partials in that case. So for G equals 1 bar 1 1, and G dot B is about 2/3 and 1/3. The 1/3 will be invisible, the 2/3 will be visible, and that's why we're seeing what we're seeing. This is copper, and this is Ni3Al at the bottom there. There's the diffraction pattern for C and B. Bless you. And then here we have a 2,2O G vector here and a 2 bar 2O vector there. And so let's now just have a look at Burgers vector determination. And what we have here are, we're going to concentrate on these defects here. Let me go back here. So those two here, say to start with, and if you look at O bar 2O, they're no longer visible. So we'd have to say this is going to be a G dot B 0 condition, this is going to be a G dot not 0 condition. You can see that they're back here, those two, and they're here in that condition there. They're out of contrast here again, and in fact they're out of contrast here. So we can build this table up here the B dislocations, why aren't we marking them? Hold on. Okay, so these are the A's here, and the B dislocations are, I chose a, well, for some reason I haven't marked them on here, the B's. But so just take a look at the A dislocations. Oh, there they are. There's the B dislocations, is here. So as we go down these various vectors, the 110G vector, which is this guy here, A and B are both in. 1 bar 10, Berger's vector is 1 bar 10 is this one here. So A is in, and that's in. Okay, don't give up yet. O bar 20 here. This is out, and that is in. Then the 200 is here. This is in, and B is out. And O bar 11, which is here. Then we have our A is out, our B is in. And for bar 101, here, this G vector, then we have A is in and B is out. And so, from this, these BA has to be 100, is Berger's vector, and B has to be 010. Sorry, not bar, 010. And essentially, if you have two outs in any given analysis, then you can uniquely define the Berger's vector, the direction of the Berger's vector. Now this is the NiAlB2 compound that these were taken in. And so these are sort of interesting Berger's vectors. This was a single crystal of the B2 compound. It was deformed at 600 degrees centigrade. And if these are the active dislocations, if they're gliding, then what it tells us is that we're not going to be satisfying von Mises' criterion, and this stuff should be brittle. But it's not. So it leads us to realize, or to think carefully, that there's probably some climb going on here, and not just glide. And so we can, because these single crystals are quite ductile, and particularly at 600 degrees C. But that's how we would do this, and of course now we can also do the trace analysis to find out what the crystallographic analysis, to find out what the directions are. And when you do that, you'll find out that these are edge dislocations. So it makes you even more suspicious that they're climbing. Okay, contrast from particles and small strain centers. Then, so this is intensity contrast from a simulated image of a particle. And notice the line of no contrast here, which corresponds to the plane that is not distorted by the strain field of the particle. So it's very clear, a very distinct image there. And you can calculate it, and the line of no contrast is basically along here in terms of the distortions around this particle. And depending on that, where you are in the relative to the top or the bottom surface, this is how the contrast varies for dark field then on the left and bright field on the right. And so this is a series then, these are all calculated images of course, and therefore different geometries of the A's and the size of the Berger's vector, and then G, the two different G's. And so you can get, by using image analysis, you can then define exactly what you have in terms of your particle. And then weak beam dark field imaging, right? So we said, right, the refracted intensity is given by this, and so this is the effective deviation parameter here. You've seen those terms before. So the refracted intensity decreases very rapidly with increasing values of the deviation parameter. Okay, so this is our effective extinction distance here, depends on our deviation parameter, or we can write it like that. And so our image widths as well are proportional to this effective extinction distance divided by 3, right? Where that's our effective extinction distance. So if we want very fine images, we need to operate at large deviations from Bragg. But the problem is, in bright field, remember the rocking curve here? In bright field, if we go a large deviation from Bragg, we get to a situation where we have very small intensities. So that's not very useful for us. So what we want is, right, the dislocation image will be very thin, which is great, but also very low contrast. And what we want to do is get something that's very high contrast if we can. So in dark field, at large deviations from Bragg, the images will be thin, but the contrast will be very significant. So if you're in dark field, so a bright image on a very dark background. So if our background is very dark at this large deviation, then any information we have from any diffraction from the dislocation will give rise to then a bright image in dark field. So, and this is very kinematical scattering because it's a very large scattering event. So an example would be if our extinction distance is 40 nanometers and our deviation parameter is, say, 0.2 nanometers to -1, then our effective extinction distance is 5 nanometers. And the image width would be about 15 angstroms compared with 130 angstroms in normal bright field imaging. So if you want to pick up, say, a fairly closely spaced couple of Shockley partials, then you're going to use weak beam dark field because then that gives you a chance to see them rather than not see them because of our relatively large image in normal bright field imaging. So in dark field, at large deviations from Bragg, the image will be thin, but the contrast will be quite significant. So bright image on a very dark background. And so the origin of the contrast, we call R is included in the dynamical theory in that way, that term. Hence contrast arises from a local change in S caused by the displacement field of the defect. And when this equals 0, this term, S plus G dot dr by dz, then the crystal is at the Bragg condition and there is strong coupling between the bright field and dark field beams. So when we have it, this term is very large, then the crystal is far from the Bragg condition, and diffraction will occur only when there is sufficient bending to bring the crystal planes into the Bragg condition. So it's very close to the core of a dislocation. That's why it's such a thin image. So determining the value of S, if you need to do that, we draw a line through the G systematic row and let the eval sphere cut through this line at NG, where N is not an integer. So what's the value of N? And then you can note, this is an interesting diagram. I think your eyes will start goggling a bit when you look at this. So G, 2G, 3G, 4G, 5G, and then up here we have 3G, bar 3G, bar 2G, bar G, G, 2G, and so on. And so it shows the positions of the Kikuchi lines for the systematic rows of reflections when 4G is excited. So 4G is excited, so that's 4G is lined up, but then you can see the rest of these start deviating. And so we say that the 3G here will actually end up on 3.5G. So from that we deduce that N is 2m minus big N, so N is an integer, refers to the Kikuchi line closest to the NG, the eval sphere intersection, and Mg is the location of the Kikuchi line as measured. And so you can then determine then from that what you need in terms of determining what the S is. So using N equals 2m minus N, and the example shown in the figure, then N equals 3 and M equals 3.1 and N equals 3.2. And so if N is 4, then M is 3.6, measuring the value for the 4G Kikuchi line, and so N is 3.2. And so then S is just given by this equation here, and so values of S for various KVs is shown here. So why would you need to measure the value of S? It's because if you're doing computer simulations of your images, then you need to have that well defined. And that's how you'd go about doing it. And setting up weak beam images, as we said before, here, what you'll do is you will set up your G strong beam bright field here, and then you'll swing this beam into the center. So here it is. It'll be very weak, but in doing so, it sets up 3G at the Bragg condition, and then we view that in dark field. So what you do then is you set up a normal, nice strong beam condition, and then swing that strong beam into the center by tilting the beam, and then you'll automatically then end up exciting 3G and view that in dark field, i.e. with an aperture. And so this is the formalization of it. Okay. So there you can see that the EVOL sphere is cutting right through the 3G situation there. And typical weak beam images might look like this. So strong beam on the bottom here, weak beam on the top. And you can get very interesting sets of images here operating in the weak beam dark field condition. So this is the 50 nanometer, 500 angstroms scale marker here. So these are clearly quite thin images. Okay, and that will do it for today. Are you going to say anything? Okay.
All right, so far we have been about elastic scattering, okay? We're going to change gears now and begin to talk about the effects of inelastic scattering of electrons. And that gives us additional information for characterizing our materials. Again, I apologize for the voice. Hopefully it'll be a little bit better tomorrow. So here. This says short version. It's still 200 slides long. So I'm not going to hit all of those, guaranteed. And I just want to spend a few minutes, maybe 15 minutes today, talking a little bit more about it. Here's the pointer. Okay. So far, we've looked at the microscope as a tool for generating a beam, creating images, creating diffraction. That's a valuable bit of information. You saw some beautiful images of defects that Hamish was showing you today. Here's another nice image of defects in a material. Now, can we do diffraction contrast on these and analyze what's going on? Yes. Can we do morphological studies on this and say, well, what do I have? I've got rectangular things, round things, square things, all kinds of stuff. We can spend a lot of time doing the defect analysis, and that'll be valuable information. But is there another way that we can get information? What if I could go up to this, and this is an engine aircraft alloy, aluminum alloy. What if I can go up to that, and if the question is, we've added alloying elements, can the diffraction contrast experiments tell us where those alloying elements are? Not very easily. However, if we use inelastic scattering spectroscopy on that same area, that image becomes that image. All right, now I have a whole new wealth of information about the solid. I can tell you where the manganese is, where the magnesium is, where the zirconium is, and very importantly, these little tiny blue dots where the europium alloy additions are gone. How do we get that? That's going to be what we're going to talk a little bit about today and finish up more tomorrow. And hopefully I can talk a little better. Okay, we're going to do this by doing inelastic spectroscopy. We're going to take the beam, interact it with the sample, and measure additional signals that come from that solid. Okay, we're going to do two kinds of spectroscopies. I'm going to first talk about X-ray energy dispersive spectroscopy, and then by electron loss spectroscopy. Right now, you have EDS spectroscopy on the machine. And correct me if I'm wrong, or not wrong, you're getting an EEL system. Yep. Okay. Okay. Why do we want to do EDS spectroscopy and a TEM? First question. Most of you probably know you have an SEM. You probably have an SEM here. Sorry. And I'm sure it probably has an EDS system on it. And you know you can put the probe on an area, measure a spectrum, and get some elemental information. What's the limit of that? The limit of doing that analysis is the fact the probe comes in and interacts with the solid, and there's multiple scattering going on, and you have an excited volume. In an SEM, on a good day with the wind blowing right, on the right phase of the moon, you might have a spatial volume of a micron or two. Okay. Can we adjust this? Yes. We can make that volume smaller by adjusting not the size of the beam, but the energy of the beam. All right. Is there a way we can increase the resolution? Well, what's the limiting factor here? This. How do we get rid of that? Chop. Cut it, make it smaller, and make it smaller. So we increase our spatial resolution. At the same time, from the SEM to the AEM, or now the TEM with a probe corrector, that probe size gets smaller and smaller. So we can change our analysis volume from microns down to sub-nanometer volumes. And with the phase of the moon right and the right sample, the perfect sample, we can even get down to atomic levels. All right. A couple other examples of that. You've seen some of these examples before. This is the catalyst particle that I showed you early on. Was it yesterday? Yesterday. So the colors have changed. All right. So the whole point is we can get a huge amount of information from elastic scattering, but not everything. In this case, we can see the precipitates. In this case, can we see the catalysts? The answer is no. In this case, we can augment the image information by the chemical information. In this case, we need the chemical information to localize where the catalyst particles are. Okay? And for those of you, and how good of a scale? This is a micron scale. That's a 20 nanometer scale. Those of you with really good eyes can see at some point we're actually looking at single atoms of ruthenium. There's another example of that. An engineered material. How many of you have heard of something called atomic layer deposition? It's a methodology of laying down literally monolayers of material. Okay? This was a fabricated test sample. And we put down one monolayer, 2, 4, 6, 8 monolayers on top of silicon. So we got silicon, aluminum oxide. Then I put a monolayer, first of manganese oxide, then titanium oxide, and then 2, 4, 6. Look at the image. In the image by itself, it's very difficult to say where something is. I can say for sure there's something here. Can you see anything here? On the other hand, this is a very quick, fast scan. Oops, the color changed. It's supposed to be blue. that's supposed to be blue. I guess it's blue on there. We can see even with 1 millisecond per pixel, I could say there's a monolayer of manganese oxide there and titanium oxide. And look very closely, you can actually see the offset because one is added after the other. So what we're going to talk about a little bit today and finish up tomorrow is we're going to first talk about X-ray generation in the microscope, then about the detectors, a little bit about the instrumentation. Data analysis and quantification is essential to understand this, and then we'll talk about a few other things that add to that. Okay, how do we employ inelastic scattering to get a signal? In the electron microscope, elastic scattering is the beam comes in and goes straight through with no energy loss. In inelastic scattering, the incident electron beam comes in, interacts with the inner shells of the atoms, and can either, if it interacts with one of the inner shells, it can eject an inner shell, and it can lose energy. That process is electron energy loss spectroscopy. Okay? When that happens, after this event, we now have a vacancy in the inner shell. The atoms don't like to be excited. Hamish doesn't like to be excited, right? He likes to be calm. I don't like to be excited, or at least I like to talk. Don't like to talk excited. What's going to happen is the electron energy population is going to redistribute itself. And the electrons from a higher order shell are going to drop down to fill vacancy and release energy. When it releases energy, that atom is going to come by and give off something, give off radiation. It can either emit a photon, in this case an X-ray photon, or it can emit another electron, an Auger electron. Okay? These are competing processes. You either get, if you have electron energy loss and you've excited an inner shell, you either get an EDS signal or an Auger electron. Okay? The spectra from these three different spectroscopies looks completely different. In electron loss spectroscopy, which is we'll talk a bit tomorrow about, we have energies that have lost electrons that have lost no energy, and then electrons that have lost different amounts of energies. We'll talk more in detail about this. In EDS spectroscopy, what we have are nice characteristic peaks. Those peaks are fingerprints. We'll tell you that bit in a moment. The two spectroscopies are complementary, and they look to be completely different. They give us different information. Okay? Where does the information come from? If we've had our incident electron come in, and we've knocked out an inner shell electron, and that primary electron now has lost some energy, we can measure that. But what's happened is this electron's lost energy because, the primary electron's lost energy because it's knocked the electron up to an inner shell. And usually it'll knock it above the Fermi level. So this electron will probe information above the electric scattering above the Fermi level. When we get an X-ray emission photon, what's happened is that electron's now jumped out and another electron drops down. What we're going to get there is information about the distribution of electrons from that state to that state. You could see that in the shape of the spectrum. Okay, let's first look at energy loss spectroscopy. So we've knocked an electron up. That electron cannot go into the filled atomic states. It has to go into a state above the Fermi level. So the electron spectroscopy is going to reflect the density of states of matter above the Fermi level. Okay. If instead, okay, so if we look at, oops, wrong guy, forward. So here's an electron loss spectrum from copper. This is copper, this is copper, this is copper, all copper. Here we're looking at the electrons come in, it's not electrons out. When we look at information about the empty density of states above the Fermi level. X-ray photoelectron spectroscopy, on the other hand, is a different process. In X-ray photoelectron spectroscopy, we're knocking photons come in, we're knocking electrons out, but we're looking at the energy distribution of these. So energy loss spectroscopy probes the empty density of states. X-ray photoelectron spectroscopy probes the full density of states. I keep hitting the wrong button. All right, so here's copper. We're probing the empty density of states. Here's X-ray photoelectron spectroscopy. It's the full density of states. They're complementary to each other. Okay? And X-ray energy dispersive spectroscopy, on the other hand, doesn't probe that. It probes the transition between state A and then between the initial state and the final state, and that's simply an energy difference. Okay. Forward. When we knock an electron out of a shell and another electron from a higher shell falls down, there's a very specific energy difference between those shells. Okay? If we knock an electron out of a K shell, electrons from higher order shells can drop down. If it goes from an L shell to a K shell, that's an alpha line. If it goes from an M shell to a K shell, it's a beta line or a gamma line. If we knock initial state out of the L, then we can get an L alpha, L beta, L gamma. Again, it's just a simple transitions. The energies of X-rays change with atomic number. Okay, as we go up in atomic number, the energy of those lines gets higher and higher. So that's a characteristic thing. The other thing that's very characteristic is the energy difference between these states. The energy difference between these states is the difference between the initial and the final states. So that's you all know that when you study from your physics courses and chemistry courses, the shells have very discrete energy levels. So we know these energy differences are very discrete. They're a fingerprint of what's in your solid. One other thing to know about the lines, the transition probabilities, the relative intensities of lines is also very characteristic. Alpha lines are always the most intense because they're dropping the shortest distance, followed by beta lines, followed by gammas and etas. Okay? Generally, so these are all normalized at the most intense is 100. So the alpha lines are the highest, then come the betas, and I've given you a range here because it varies slightly with atomic number. Same thing holds for the L's and the M's. There's an example of a specimen. It's a semiconductor, yttrium, barium, copper oxide. So I picked this example because it shows a nice example of everything. First of all, we have the copper K line, the copper K alpha, and the copper K beta. Look roughly at that ratio. It's about 1 to 10, which was similar to that. So 1 to roughly 10. Okay. Oops, forward. So we got the copper K. If we have a copper K, we also have a copper L. Copper L here's a little more complex. We'll talk about that later. The other thing is we got a yttrium K. Now, higher atomic number, higher energy. We still have that ratio, roughly 10 to 1. Okay. Barium's a much higher atomic number. Okay. In barium, we're going to be looking at the L shell intensities. Why? Because barium's up here. We're going to be looking at the L's because I want something in this energy range. There is a barium K. It's up here somewhere at a much higher energy. Okay? And that we don't see in, we don't see in the spectrum. It only goes to 20 keV. You can measure spectra at much higher energies. Most people tend to work in the range from 0 to 20. Occasionally they'll go to 40. It's very rare for somebody to go higher. Oh. One last thing. If you have a K line, you will always have an L. If you have and if possible, an M. Okay. Why is that? Because the energy of the beam we're using in our microscope is sufficiently high that it'll ionize things. Remember, with 10, most of you will probably be running at least 100 kilovolt energies. Some will be running at 300 kilovolts. At 300 kilovolts, you'll excite the entire periodic table. You may not detect it because the lines may be way out here. Or you may be looking at very high family lines, L's, M's, N's. In addition to characteristic energies, we see a spectrum rides on top of a background. That background is also due to an inelastic scattering process. It's the incident electron interacting not with the inner core electrons, but the nucleus. It's called Bremsstrahlung, breaking radiation in German. Okay? And it's due to the electron beam coming down, interacting with the nucleus. This Bremsstrahlung radiation is the same thing that's generated in the synchrotron when the electron beam goes around. Okay? That background shape is very characteristic. And I want you to remember this, because when you're in a lab, because looking at the background, you can tell if everything's working right or not. So first of all, that background will be a continuously decreasing intensity. It'll stop at the energy of the electron beam. Okay, if you're on a 300 kV electron beam, you'll never get there. But if you're in an SEM, you'll see that point. It'll continuously rise as we go down in energy, but in the real world, we never see it going up continuously. Here's an example of an experimental spectrum from beryllium. Okay, it starts out low, starts coming up, and then drops off. It's dropping off here because their detector is inefficient down there. Again, we'll talk about that. Okay, the shape of that background goes roughly as 1 over the energy, and actually goes as the energy difference, incident beam minus the energy you're looking at, divided by the energy, times the atomic number. Okay, so what does that tell you? The background is atomic number dependent. Okay, so higher Z materials also have higher background. Lower Z materials have lower background. And there's always a cutoff. Here's that other spectrum we were looking at just a moment ago, but I've just blown it up a little bit. So we can see that continuously decreasing background. Okay, we can see it's doing something funny here. Why didn't it drop all the way down? There's too much other information here that we can't see it. Okay, but you can see it's starting to drop off. The other important thing on this background, I want you to remember this, that background should be, after we get that initial dump, should be going down continuously. Okay, you can use that. Here's the background. Now this is a log scale now. As a function of energy. You notice I'm going very high in energy now. And it's going down continuously. That's great. Look at this background. It's not going down continuously. There's something strange going on here. What's happening is there's a fault in the system, and we're actually getting electrons into our X-ray detector. So if you see the background and it's not dropping off, you know you've got a problem with the system, and you need to investigate that to make sure we're okay. Okay, I'm going to spend just a few more minutes talking about the different detectors, and then we're going to stop for today. All right, there are a whole slew of different kinds of detectors. There's wavelength dispersive spectrometers, energy dispersive spectrometers, and there's 2 types that you will generally see. The lithium drifted silicon detectors, if you're an older system, or the newer ones, the silicon drift detectors. We're not going to talk about these guys. We're not going to talk about the germanium detectors. I don't believe any of you will ever buy one of these. These are about $500,000 a piece. These are usually high energy physics. We'll talk a bit about some of that data. So I'll mention wavelength dispersive spectrometers because that's a traditional detector. And they operate very simply. We can recognize them very easily by looking at an instrument. Okay? Here's an SEM, here's a TEM. The lithium drifted silicon detectors can be recognized very easily by the large dewar that's on the side of the microscope. That dewar is generally filled with liquid nitrogen. Okay? So there's one there, and there's one there. In the newer STD detectors, that dewar is gone. We'll talk about that. Wavelength dispersive detectors are huge monsters. Okay? They're mechanical devices. You rarely see them on TEMs. Okay? Can it be done? Yes. Is it done traditionally? No. So all of the energy dispersive spectrometers, whether it's a Cili detector or an STD, work on the same principle. Okay? There is a specimen. It hits by an electron beam. X-rays come off. They hit the detector. We'll talk about that in a minute. A signal is generated, amplified, and a spectrum is produced. Was there a question back there, or no, you're stretching? That's fine. I see a hand up. Wavelength dispersive spectrometers work on the principle of Bragg's law, just like we talked about Bragg's law for scanning with electrons. You can get Bragg's law for scattering of X-rays. Again, the same principle. Electron comes in, X-rays come off. This time they hit a crystal of known spacing. They diffract off, and a detector measures those. Okay? This is rarely used in the TEM today. The reason is these are generally large devices. They're complex mechanical devices. They have excellent resolution, but they're complex devices. The focus is dependent on height. They have limited solid angles, and they're serial detection. So generally, you won't be using those. Oh, and I'm sorry, did I skip some? I skipped the slide. Yeah, the nice thing about EDS detectors is they're simple. They're nearly operator independent, not quite, but nearly. They can have very large solid angles. That's an important factor for today. They're virtually specimen position independent. There's almost no moving parts. And they have nearly parallel detection capabilities. The downside is they have poor energy resolution. They have mediocre peak to background ratios, and the detection efficiency depends on the energy of the X-ray. All right, I'm not going to spend any time talking about the wavelength dispersive in the TEM. That's the modern one. This is the point I want to make about a comparison between an EDS spectrum and a WDS spectrum. Same material, two different detectors. This is EDS, this is WDS. Again, same thing here. EDS in a line, solid in WDS. You see the huge difference in energy resolution, okay? Well, you say, well, that doesn't matter. I can still tell there's chromium there. I can tell there's iron there. Absolutely true. But what about something like a barium titanate material? The barium L and the titanium K almost completely overlap. Not quite, but almost. In an EDS spectrum, you don't have the resolution to resolve that. In a WD spectrum, you can resolve that. Okay? Is there another solution? Yes, EELs, but that'll be tomorrow. So we won't spend any more time about this. I already described it. We're mainly going to be talking about EDS-type spectrometers. Again, I told you can recognize EDS spectrometers very easily. On the column of a microscope, you usually have a large dewar that can do two things. One, it can be a cold trap to cool down the cold finger in a microscope, but they're just also used in a lithium-drifted silicon detector to cool the detector down. Today, silly detectors are getting fewer and fewer, okay? Everybody's changing to the STD or silicon drift detector. These devices don't need cooling, but they don't need liquid nitrogen cooling. They operate at about minus 30 degrees C. That can be done with a Peltier cooler. What's good about that is Peltier cooler has no moving parts. You don't have to continuously refill liquid nitrogen. You don't have to remember it. And they're very rapidly cooled and warmed up. With a lithium drifted silicon detector with all the nitrogen, if you need to warm up the detector, you got to dump the nitrogen. You got to wait for everything to cool. It takes a long time. And if somebody vents the column, what's going to happen? You got a thing full of a cold finger of liquid nitrogen. You vent the column. What's going to happen in a day like today? And the humidity inside, you're going to get water vapor condensed around the cold surface. So it's not a great idea. In an STD, they warm up very quickly. You unlikely will get water there. You can, but you may not. All the detectors are very similar. Recognize this one? This was the first X-ray detector I ever put on a column of a microscope at Illinois. We had to design everything back then. We bought the detector, but there was nothing else available. Okay, the detectors, I don't care which one it is, are usually enclosed in some kind of environmental housing. Why? Because the front of the detector is usually cooled. Even if it's an STD, it's cooled still. We have an environmental housing that surrounds the actual detector. This is a lithium-drifted silicon detector. It's literally a piece of silicon. I'll show you a picture of that in a minute. Behind it is a field effect transistor. The X-rays come in. They end up in the crystal. X-ray signal is generated. The reason for cooling these to liquid nitrogen is to reduce the noise in the FET. You'll see why in a minute. On the front of a lot of these detectors is some sort of environmental protection window in case you dump the column. Okay? You really don't want it. Back when I first started, this is actually a picture in front of that, one of these. They had Berlin windows on the front, typically about 8 microns thick. Nowadays, we have different kinds of windows, or we can actually run windowless. The way we make a silly detector is we take intrinsic silicon, we diffuse lithium in it under reverse bias, we segregate it, get an intrinsic zone, we take that crystal, we chop off the front and the back, and now we've got a piece of intrinsic silicon with a P and N on the other side. Think of this as a capacitor. Okay? How do we get signal? Well, let's see, I think that's the next slide. No, let me go a little bit further. This STDs are, again, slightly different. They're a very small chip. The difference here is in the lithium drifted silicon detectors. These guys are typically 3 or 4 millimeters thick. In an STD, it's a very thin silicon chip, about 0.3 or 0.4 millimeters thick. It's intrinsic silicon. It sits on top of a Peltier cooler. The nice thing about these things is the Peltier cooler cools them, and they're very small. They can be fabricated in lots of different shapes and sizes. You can have round ones, rectangular ones, different shaped ones. You have a Super X system, right? That's a detector. This is what the detector for a Super X looks. That's actually a detector from a Super X detector. I take things apart. I think Hamish will vouch for that. All right, the STD is, again, very thin. What happens in the STD, rather than having one big capacitor, what happens is we have a back contact, the X-rays come in, they dump energy into the silicon. When it dumps energy into silicon, it creates electron hole pairs. On the other side of the silicon, not the side that the X-rays come in, but the back side, there's a set of voltage rings. We set up a voltage ramp across the back of that, and the electron hole pairs get attracted to that voltage ramp, and they travel up this to the anode. What do we see when an X-ray comes in? A burst of electron hole pairs gets generated, and a small bit of charge comes up here, and we get a voltage pulse. I think that's my next slide. Yes. And I think one or two more slides, and then we're going to stop. All right. So what happens? How do both the silly and the STDs work on the same principle? We've got a piece of silicon here or here. An X-ray comes in and creates electron hole pairs by N-ionizing. Now, in silicon, it takes 3.8 EV to create one electron hole pair. Okay? That's characteristic for silicon. So if you have a 10 kV X-ray, it'll generate 2,630 electrons, or 4 times 10 to the minus 16 coulombs. Very specific. So what do we want to know? How do I know the energy of my X-ray? All I have to do is measure the charge that's built up here. So an X-ray comes in, creates so many electron hole pairs. I measure the charge. I know what the energy of the X-ray is. That's how the detectors work. What's typically done is that X-ray comes in, the charge gets built up, and then we use some sort of a measuring device to measure how much charge. In these silly detectors, there's the FET. It's cooled down because that's a pretty small charge. Kind of electronic noise disrupts it. So you cool it down to make the FET more efficient. And the same thing here, you cool them down. It doesn't have to be as much. So an X-ray comes in, what happens? We get a small charge pulse or voltage pulse. The height of that pulse is directly proportional to the energy of the X-ray. Another pulse comes in and jumps up. Another pulse comes in and jumps up. Between pulses, what we do is we want to measure the voltage jump. We want to know that height. That tells us what the energy of the X-ray is. So your system is actually just a series of steps. Okay? And we're measuring pulse heights. We have a pulse height analyzer. That's what an X-ray analyzer is. It's a pulse height analyzer. It's measuring these. It's measuring the pulse height. The pulse height over a series of time. The longer the time we take to do that measurement, the more accurate we know the energy. Okay? And after a certain amount of time, we have to reset everything because it's a capacitor. You got to discharge it. Okay? That's how the system works. Let's see, what's the next slide? Okay, so the X-rays come in. There's actually, yeah, let's finish. Two more slides and then we're done. So the X-rays come in, they enter the crystal, and we get pulses coming out. How good is the detector? Well, the detector is only as good as the ability to get that X-ray into that point. I already told you some detectors have a window in front. I also already told you that these things are semiconductor devices. There's electrical contacts on the other side. All of those stop the X-rays from actually getting into the region that I want. Okay? So there's an intrinsic energy barrier to getting those X-rays in. Okay? And that's a simple absorption effect. You all know X-ray absorption. An X-ray goes through a material. It gets decreased exponentially according to whatever the material is and the thickness of that material. So it's an exponential decrease. The higher the energy, the easier it is to get in. Okay? So this is what a typical efficiency curve for X-ray energy is. And now I'm down at the low energy end. Very low energy X-rays can't get through the window. So the energy drops off, the efficiency drops off to zero. Remember the background curve I showed you? It came up and then dropped down. It's dropping down because of this effect. If I change that window, if I go from a beryllium window to a polynomial window to no window, that efficiency gets better. Great. Why doesn't it go to 100%? Well, it still has to get through into the silicon. So at a certain point, you can't get any better than this. As the energy gets higher, it's easier for the X-rays to get through. It goes up to near 100%. Okay? But there is a problem. If the energy is too high, what's going to happen? The X-ray is going to go right through. And so what will happen is at the high end, the efficiency, so this part is this part. This part is the high energy end. And if the X-ray energies are too high, it'll go near 100%. And then it'll start going through the crystal, actually right through into the back. Think of all the lead shielding you have on your microscopes. The high energy X-rays are generated. They're going to go right through the crystal. And this intensity is going to drop off. Depending on the thickness of your crystal, your high energy efficiency is going to be either good for really thick crystal and gets worse for thinner crystals. The old silly detectors at 3 millimeters thick were near 100% out to 20 keV. The new SDDs tend to be around 0.3 millimeters. So they start dropping off about 10 keV. And by the time you hit 20 keV, they've lost a lot of efficiency. Doesn't mean they're not working. No, they still work. We just have to realize that. Why am I going through this? It's important to understand this curve when we ultimately try to quantify data. Okay. We're going to stop there. No, one last thing. And I already told you about changing the window. Changing the window increases the efficiency. I'll just show you. This will be the last slide. Yeah, I think it is. Yeah, last. So the very dark curve is a beryllium window detector. We see the nickel K, high energy X-rays, 100%. We see the nickel L. But this was a nickel oxide sample. Do we see oxygen? No, because the efficiency's gone down. If I remove the window and go to a Windows detector, not only does the efficiency for nickel L increase, more efficient, but we're also starting to see low Z elements. All right, here's a more modern detector. This is my new detector on my machine. Not only, and now I'm going to go down very low in energy down here. Not only can we see oxygen, carbon, I can go all the way down to beryllium. Okay? So in a modern machine, you can do almost the entire periodic table. You can go from beryllium. I've gone from beryllium to uranium. Now, you can't do hydrogen and helium. Anybody want to tell me why? Okay. Hint. In order to get an X-ray, you have to have electrons in a shell above. Hydrogen and helium only have a K shell. Only the first shell, one S shell. If you knock the electron out, there's no electron to drop down. Hydrogen and helium do not emit X-rays. So you can't do EDS analysis on hydrogen and helium. There are other techniques we can use. Okay, so when we come back tomorrow, we're going to talk about artifacts in spectra and go on from there. So let's call it a day, okay? Thank you. All right. So we know where we are. And hopefully I can talk a little bit better.